So good afternoon all of you. Welcome to this session on revision to PYQs of fluid mechanics. Okay. So normally every time I say that before you go for the GATE examination, solving PYQs is very important. Okay. Because it happens that because GATE being organized for last 34 years. Okay. So you'll see that majority like 60 to 65% of the marks, like out of 100 marks, 60 to 65 marks you can solve very easily if you solve PYQs and then go to the exam. Okay, because many times we see the patterns keep repeating. Okay, and then the questions were very similar many times. Okay, so very few times you see a completely different question. So this PYQ session is really important, so don't leave the session until this session gets finished. Okay, because when you have the PYQs, okay, when you solve PYQs you'll get the complete idea on how the questions are being come. Okay, because I may said so many new questions, I have made tough questions. Okay, I can practice so many questions, but at the end of the day the actual level of the GATE examination is decided by these PYQs. Okay, so let's solve these PYQs and chalo, let's start the session, of course. And if some of you are seeing me for the first time, then I would like just like to introduce myself very quickly. My name is Vinay and I'm from the mechanical team of PW, and I have GATE All India Rank 4 in 𝐂𝐸, and then previously I was working as an officer at the HPCL, and I was also a scientific officer at BARC previously. Then ISO I have selected as a scientist. Okay, and then my MTech specialization is in thermal engineering, and these are the subjects that I teach generally. Okay, engineering, maths, fluid mechanics, thermodynamics, heat transfer, basically the thermal domain subjects including mathematics. Okay, so we'll look at this. Normally in today's class we'll solve questions related to the PYQs of this fluid mechanics. Okay, and if you feel that I can help you out at some point in clearing the exams, or if you feel that you need some guidance, then you can definitely scan this QR code. This is the link for the Telegram channel. Yeah, so ऊपर से आज English ऊपर से गया क्या? Nothing like that. I'll do see, you can read the question, we'll solve, and I'll give the explanation very slowly. Okay, no issues. Okay, so then you can scan this QR code and definitely you can get into the Telegram channel. There are almost like 2,300 plus people are there sharing thoughts and discussing the things. So if you are in the loop, you will also get habituated to solve the questions. Okay, so let's start solving the questions, of course. So the first question which we see, it's a NET type of 2018. So let's see, a solid block of 2 kg mass slides steadily at a velocity v along a vertical wall as shown in the figure. A thin oil film of thickness h, this h which is 0.15 mm, which is very small. Okay, so this 0.15 mm provides lubrication between the block and the wall. So there is a wall and there is a block, and this oil film is providing the lubrication. Okay, then the velocity distribution within the oil film gap is linear. So you can see there is a linear velocity profile as shown in the figure. The dynamic viscosity of oil is 7 into 10 power minus 3 pascal second, and acceleration due to gravity as 10. So in this question they have given g as 10. Neglect weight of the oil. The terminal velocity v of the block is dash. So let's solve this question. Solution. So you have this wall and of course the block as well. Okay, so you have the wall and the block actually. So you have the block as well, and here you have the oil film which is present like this. Initially if you release this block from rest in Mach revision also, I have told you, if you take the velocity of the block with the time, you will end up with an increasing profile and then coming such steady state. Okay, so this is V steady state actually, correct? This I have shown you in the Mach revision classes. Then if you in this case see, this clearance is h, this clearance is h, and you have some mass m for example. Okay, then let's see, for uniform motion of the block, for uniform motion of the block, sigma f acting, let's say maybe y in the positive direction is plus y. Okay, so you can see this might be a y direction, so sigma fy should be 0, correct? Only then the block will not accelerate, it move at. Question को read करना भी time दे दीजिए please. I have read the question, no? Okay, fine, ठीक है, we'll go slowly. So sigma fy is equal to 0. There is a block sliding on this oil film. What is the terminal velocity of the block? That's the question. Okay, so this implies if you draw the free body diagram of the block, you'll come to know that this block has some mass, so obviously some weight, and then because it's in contact with the oil, it has the viscous force which is acting on the block actually. And if these two balance each other, in that case the block moves with uniform velocity. Okay, so sigma Fy is equal to 0, so Fv minus mg is equal to 0, so the viscous force is equal to mg actually. Now how do you get the viscous force? Viscous force is nothing but shear stress into area. So shear stress, viscous shear stress into area of contact is equal to mg. Okay, so this AC, area of solid oil contact. Okay, and how do you get the velocity profile? This shear stress mu into velocity gradient. Since the velocity profile is linear, you know at this point, okay, so if you take the velocity profile here, since this wall is static because of no slip, the fluid layer has also zero velocity. Here the block is moving at velocity v in this direction, so definitely this oil film that's in contact with the block will also move. So there is a linear variation, the gap being very small. So let's say this is v, so v divided by h into AC is equal to mg. So you want this terminal velocity. Okay, so v terminal, let's say v terminal in this case is equal to mgh by mu times EAC. That's all. It's a very simple question in fact. So this would be the expression for the terminal velocity of the block. Okay, good solve karne ko. Okay, I'll give this. So now we'll see the values. Okay, so first by reading the problem we understood the physics, what's going on. So let's see, V is equal to mass. So what is the mass of the block? A solid block of 2 kgs mass, so m is equal to 2. Gravity they have given you, it's 10, so this is 10 into h. The thickness of the oil film is 0.15 mm, so 15 into 10 power minus 5 meters, because I'll write everything in SI units. Mu is 7 into 10 power minus 3 Pascal second, so 7 into 10 power minus 3 Pascal second. Area of contact, so what is the area of contact? The surface area of the face of the block in contact with the oil film is 0.04, so 4 into 10 power minus 2, that's all. So this is what you get. Even in fact you will observe for many questions in gate, what actually come in gate, you don't even need the virtual calculator. Okay, sorry, Gaitaran. Okay, thank you. Yeah, so let's see, if you simplify this, first 10 power minus 2, 10 power minus 3, this 10 power minus 5 will go away, then 4 cancel this 20 5 times, 5 15s are 75 by 7, so Vt is equal to 75 divided by 7. So obviously 7 table can cancel this, 10 times 0.5, so 7, how many decimal places we need? Cut to 1 decimal place, next digit is 1 almost. Okay, so this implies Vt is almost 10.7 meters per second, that's all. Okay, so this is the terminal velocity with which the block falls down. Clear? Thanks, Gaithan. So is this question okay to all of you? It's a simple static balance. See, first, rather than doing the equations, substitutions, simplifications and all, for any problem, when you read the problem, you should understand the physics, what's happening inside. Okay, so once you understand the physics, then putting physics into math equations is very simple. Okay, clear? Maybe I think Bhagat Billa wants me to write given data. Okay, I'll write from the next question. Okay, but this question, it's a very straightforward question. So 10.7 is the value. Fine. So let's quickly go to the next question. A pressure measurement device fitted on the surface of the submarine. So it's a basically 2021 numerical answer type question. A pressure measurement device fitted on the surface of a submarine located at a depth h below the surface of the ocean reads an absolute pressure of 4.2 megapascals. The density of seawater is 1050 kg per meter cube. Atmospheric pressure at the sea level is 101 kilopascals and the acceleration due to gravity is 9.8. The depth h means basically the depth at which we have the submarine. Okay, if you take g equal to 9.81, it's out of range. Yeah, see, I'll tell you one thing, guys. In questions, okay, when you read the questions, these constants like g, characteristic gas constant in thermodynamics, okay, or Young's modulus of steel, maybe in design. If they, you can assume this as 10 or 2 into 10 power 9, these kind of values only if nothing is given in the question, okay. Sorry, if they are mentioned in the question. If nothing is mentioned, you should take the standard values like 9.81, 2.1 into 10 power 9, these kind of values, okay. So generally they'll give you in the question, like you see in GATE, each and everything will be clearly specified, and if something is not specified, for G you take 9.81, okay, and for this characteristic gas constant you can take 0.287, these kind of values, okay. So chalo, let's solve this question. Given, now people will be happy, I think. Chalo, given device fitted on the surface of a submarine located at a depth h, depth is equal to h, okay. Absolute pressure at that point P at h is equal to 4.2 megapascals, okay, good. Then density of sea water is 1050 kg per meter cube. Atmospheric pressure, so P ATM local is 101 kilopascals. Be careful guys, this is in megapascals, this is in kilopascals, okay. And G, in this question they have given 9.8 meters per second square. Clear, okay. The depth h of the submarine is 417.55, 0.4178 meters. Definitely it's not 0.4178 meters, okay. It's like half meter. If I myself stand in water, definitely half of the meter gets filled and I don't experience this much pressure, okay. See, I'll tell you guys, whenever you get some calculations, okay, have a physical feel for the calculation. Like let's say for example, I'm not pointing anyone, but I'm just telling you to avoid mistakes. If you get 0.417 for example, just before entering the answer in the keypad, just think 0.4 meters is like 40 centimeters, which means if I, let's say if I go into water until my knee depth, okay, then the 40 centimeters is already inside the water. Will my feet experience this big pressure, 4.2 megapascal pressure? Let's see if I start walking into water up to my knee height, okay, then will I start experiencing this 4.2 megapascal pressure at my feet? No, correct. So these are some small things which make you avoid by entering the wrong answers, okay. So please check these things. Now let's see, you have a submarine and let's say you also have a free surface, okay. So you have a free surface P ATM local at this free surface, and let's say this is the depth of the submarine, it's h. Then clearly this pressure at this point P, if you call this P, then P is given as 4.2 megapascal. So we have from manometer P, of course there is movement of fluid in the sea, but as a bulk we are taking as a static fluid, okay. So P at h is equal to P ATM local plus rho water G into h, okay. Let's write everything in SI units. P at h is 4.2 megapascals, so 4.2 into 10 power 6 pascals, okay, because you know this is given in megapascals, this is given in kilopascals, and this would come in pascals, so that's why units is very important, okay. So P ATM local 101 kilopascals, so 101 into 10 cube plus density of water, this is sea water, so 1050 into 9.8 into h actually. So now you can get h from this. So the depth of the submarine in meters. Fine. So let's, you can perform the calculation using a simple calculator. So 4.2 into 10 power 6 minus 101 into 10 cube. So this divided by 1050 into 9.8. That's all. Okay, because they have given G as 9.8. So equal to 398.34. 398.34 meters is what I'm getting. You're getting different value. Many of you got 417.5, but I'm getting 398.34. Which is correct out of these two? You guys did not convert this, is it? That's why maybe you're getting 417. Density गलती है ना? Yeah, obviously you should not take density of water as 1000. ठीक है? You should have, because obviously sea water has so many dissolved salts, so the density of the sea water would be slightly heavy, means high than compared to the normal fresh water. Okay, so 398.34. So nearest integer is 398 meters. That's all. Round off to the nearest integer. So I would have entered 398. A straightforward answer. Okay, those who have done 417.8, either they have taken this as 1000 or they might have forgotten this conversion. One of these things they might have done. Yes. Okay, so you should be careful. It's a 1 mark question, I think, given that year, 2021, long back, maybe 3 years back. Chalo. Let's solve this. An inverted YouTube manometer, 2016 GATE paper. So an inverted YouTube manometer is used to measure the pressure difference between two pipes A and B. Okay, so this is A and this is B, of course. Then as shown in the figure, pipe A is carrying water, is carrying oil of specific gravity, and pipe B is carrying water. The densities of air and water are 1.16 kg per meter cube and 1000 kg per meter cube respectively. The pressure difference between the pipes A and B is dash kilopascals. Acceleration due to gravity G is 10 meters per second square. Okay? 398.34, correct. Yeah. So let's solve this question. Solution. So clearly we have the diagram. So let's apply the concept of manometry. Okay. So if you see manometry, in inverted tube manometers, we should go for the highest interface. Okay. And normally in the common manometers, you will go for the lowest bottommost interface. Here we go for the topmost interface. Okay. This air is in static condition. So clearly, if you make points 1 and 2 here, from manometry, this P1 should be same as P2, correct? So how do we get P1? Let's see. Inside this manometer, everything is in static condition. Okay. So if pressure at this point is A, this is a static fluid. So clearly the pressure at this point is also PA. Okay. So the pressure at this point is also PA actually here. So we are starting at this point, but from here to here the pressure is same. So PA. Then from here, let's travel up to this point. So we have this oil all over this 200 mm length. So minus, you are going up. So density of oil into G into 200 mm. So 20 centimeters. So 0.2 meters. Minus from here to point 1, you have air, and this air column is 80 mm. It's very small, but let's consider rho air G 80 mm is 8 centimeters. So 0.08. So you touched P1 actually. Okay. Now coming to P2. So how do you get P2? If this is PB here, then ultimately this location here also it is PB, and then you have a water column of height 100, 200, 300 and 380 mm of water column. So PB minus, because you are moving up, density of water G into this is 380, so 0.38 meters. So this is the equation from simple manometry. Okay. So what about PA minus PB? That's what they're asking. The pressure difference between these things, PA minus PB. So PA minus PB. Okay, they did not give, they want the absolute value. Okay, because they're just asking the difference between these 2 points. So magnitude. Okay, so PA minus PB is equal to density of oil into 0.2 plus density of air into 0.08 minus density of water into 0.38, this whole multiplied with G. So we got different values now. Let's substitute. So this gives you density of the oil. Specific gravity of oil is 0.8. So this is 800 into 0.2 plus density of air 1.16 into 0.08 minus density of water 1000 into 0.38, this whole multiplied by 10. Now can someone tell me what would be the units of this answer? What are the units of that answer? Anyone? You have done some calculation. What will be the units? Pascals. Okay. So one caution I'll tell you, before doing the calculation, always write the units. Okay. So we'll do the calculation later, but first write the units, because make this a habit. I'll see many times students do the full calculation but end up entering the answer in wrong units. Okay. Loss. So please don't do that. So if you have this in pascals, then you can convert to kilopascals, because the final answer is expected in kilopascals. Okay. So let's see, 800 into 0.2, 160 plus 1.16 into 0.08, it would be very small, of course, 16 into 0.08, because that's the air column. So this value minus 380, so minus 380 into 10. So this is in pascals. So magnitude, if you take magnitude of pressure difference, this is 2199.07. So this is in pascals. So in kilopascals, 2 point, how many decimals you want? Okay, nothing is mentioned. So 2.199. Okay, so 2.2 you can say. So 2.2 kilopascals is the pressure difference. Okay. Yeah, that's in pascals. 2199 is in pascals. So 2.19 is in kilopascals or 2.2. Okay, a simple straightforward question from the inverted tube manometers. Okay, it's fine to all of you. Everyone, type it in the chat box. Is this okay to all of you? A very straightforward question. There's nothing very complicated or some hidden things. So let's go to the next question. So this is the question. It's in 2023. The figure shows two fluids held by a hinged gate. Okay, so there is a hinged gate by which these two fluids are held. The atmospheric pressure is PA is 100 kilopascal. So here it's PA. On the other side of the gate also it would be PA. The moment per unit width about the base of the hinge is dash kilonewton meter per 1 meter width. Round off to 1 decimal place. Take G as 9.8. Okay, so let's solve this question. Given, it's a very straightforward thing. There is a gate. Okay, so there is a hinge here. There is a hinge at this point. Hinge at this point. Okay, and there is density, fluid of density 1000 kg per meter cube and 2000 kg per meter cube. So let's see. This is row 1, let's say 1000 kg per meter cube, and this is 1 meter, and this is row 2, which is 2000 kg per meter cube. Okay, and this would be 2 meters fluid column. Now you want to calculate the moment of this forces about this hinge point. Okay, so what is this hinge point? Let's call this hinge as A. Okay, so you have this point A. Now ultimately here you have PATM, and here also there is PATM. So we can apply all the hydrostatic formulas what we know. Now first let us talk about this guy. So this fellow height is 1 meter. So what would be the, if it are the free body diagram, normally width of the plate means perpendicular width is 1 unit. Okay, so first you have the hinge reactions Rx and Ry at these locations, Rx and Ry at this hinge. Then you have hydrostatic force, say FH1 for example, due to the first fluid. Okay, and obviously due to the second fluid you have at some different location, say FH2 of course. So this is FH2. Now firstly we want the moment. Okay, so if you want the moment, what you can do, if you call this point A, okay, and this free surface point, so let's say this is the free surface point for example to which you have the fluid, so let's call this B. You want this distance A first, and also, or else maybe I'll do it this way. So you want this distance A, and also you want this distance B of course. Okay, so now if you take the moments, sum of the moments due to hydrostatic forces is equal to FH1 into B plus FH2 into A. So these are the moments. Okay, now using the knowledge of fluid mechanics, let's get this moment arms and also the forces. So first FH1. So if you look at FH1 in this case, if you draw the side view of this, you would get something like this. Okay, so this is 1 meter into the plane of the paper, so you will see side as 1, this is also 1, and the center of this is somewhere here. So let's say G1. Then FH1 is going to be rho 1 G, you call this area to be A1, so A1 into H1 bar. So if you do this calculation, 1000 into G into area. So what is area? 1 and per unit width. So 1 into h bar. So which is half. This is in pascals. Okay. So this can be written as 500 G pascals. Okay. So let's keep it that way. Then coming to B actually. So what would be B? Can I write this B as, if I call this distance from the free surface as h1 star, this total length is 3. So can I say 3 minus h1 star actually? Yes or no? And normally all of us know it's a rectangular plate. So if you see the depth of center of pressure, it is 2h by 3 from the top. Okay. So if you have 2h by 3, then 3 minus 2 times 3 into this full length of the first portion is 1. So this gives you 7 by 3 meters. So this is going to be the value of B. Is this okay till this point? Yes? So come on guys, please type in the chat box. Is this clear to all of you till this point? Yeah? Now let's see. Okay. Then let's see F2. So what about FH2 now? FH2 is nothing but, similarly if you project this other part of the area, okay, so this is the second part of the area. So you have A2, this is G2 let's say, and this height is 2 meters. Fine. So if this is 2 meters, please once repeat. Yeah, this hydrostatic force is as per this, and B, this h1 star, depth of center of pressure for rectangular surface being vertical, is 2/3 times the height of the, or the depth of the plate basically actually. Okay. So 7 by 3 h. So FH2 is nothing but, can I say this as pressure at the location G2 into area at 2, correct? Because if you calculate the pressure acting at the centroid for this plate into, if you multiply this area, you will get the hydrostatic force. Okay. So what is the pressure exactly at this area? So the pressure at this point is 1000 times rho1 G h1 plus rho2 G h2. So till the centroid you have 1 more meter, this value multiplied with the area A2 actually, and A2 is how much? 2 times 1, so which is 2. So this gives you 1000 plus 2000, 3000 into 2, 6000 G actually. Okay. So 6000 G is what? This is not Pascal, sorry, this is newtons. Okay. This is newtons, this is also 6000 G newtons. Okay. Now calculating the depth of center of pressure. So how do you calculate the depth of center of pressure here? Come on, tell me. Any idea? At what point this hydrostatic force keeps acting? Anyone? You know that this is a portion and this is the liquid. Okay. So this is the liquid, of course. If this is the liquid, then, but this surface is not at free surface, correct? This surface is not at free surface. This is the free surface actually, but this is not at free surface. So how do you calculate the center of pressure in these examples? We assume it exists downward side. Of course, I know that it exists downward side, it exists somewhere here. Okay, that's known to you. But how do we calculate that? Let's see. So if you call this H2 star, for example, okay, H2 star, I'll teach you one simple concept. Okay. For example, if you have a gate like this, okay, and you have liquid, so here this side it is PA, but the formulas F is equal to OG A bar, or basically this h bar plus I xx sine square theta, whatever the formulas you have for the hydrostatic force, they are valid only if this is free surface. But let's say if this is not free surface, okay, then what you do? How to calculate the H star? We construct a liquid column, imaginary liquid column. Okay, so we construct an imaginary liquid column of height, let's say x, for example, such that this x is equal to P1 by rho of this fluid into G. Okay, then you'll again get back PA, correct? Because as you move up, let's say for example, if this fluid extends beyond, then as you move up, you will again touch somewhere this PA, correct? And you can apply your formulas of OGFG, H bar, then formula of H star, all these things if you are measuring the H's from the free surface. Okay, so if this is your free surface, what is the pressure at this location? Initially, P1 is equal to 1000 into G into 1. So therefore, what would be X? Gauge pressures. Okay, so 1000 into G into 1 divided by rho F2, which is the density of the second fluid, into G, so which is half actually. So which tells you this is half. Then the depth of center of pressure, sorry, the depth of centroid of this surface from the free surface, this is nothing but x plus, if you call this length as 2 meters, then half of this, so which is x plus 1 meters would be the depth of centroid from this hypothetical free surface. Then again you can apply all your formulas. Got it? So if you in fact you can see, if you calculate OFGA into H bar as per this formula, you will get the same answer, like 6000 Z is what you would get, of course. Okay, like if you want, you can see, if I calculate using this formula, the hydrostatic force FH2 is density of second fluid G area into H bar. So this is 2000 into G into area, 2 into 1 into depth of centroid from this hypothetical free surface. X is half and this is 2, of course. So 1 plus half, 1 and half, so 3 by 2, 6000 G. 6000 G actually. That's what even you got here in this case by this calculations. Got it? Did you all understand? Whenever a surface is not at the free surface, you should you should construct an imaginary fluid column of height x such that this surface at height x is exactly at PATM. Then you can apply the formulas. Is this okay to all of you? Because I still remember that year many of our students has not done very well with this question because they didn't practice this enough. But of course we teach them in every places, like paid batches, in YouTubes, everywhere, but people don't put enough focus at the end. Got it? Now let's calculate H star in this case. Okay, so what would be H star? You know the formula of H star 2 from this free surface. Okay, so if you look at H star 2, H bar, so H bar is x plus 1, so which is 1 and half. So H bar in this case is 3 by 2 meters. Okay, so this is 3 by 2 meters. Now if you calculate this H star 2 in this H star 2, okay, from this free surface, you would get H2 star 2 is equal to H bar 2, which is 3 by 2 plus, it's a vertical plate, so moment of inertia of this complete figure. Okay, so this is depth of centroid H2 bar, okay, plus moment of inertia about this centroidal axis, for example. Okay, so we have done 3 by 2, so then we need not take this full area, sorry, this part. Okay, yeah, so if you look at this area which you have the x axis, so this is 1 meter and this is 2 meters. Clear? So you have B d cube by 12 into B d cube by 12. Okay, so this is B d cube by 12 into area 1 into 2 into H bar, which is 3 by 2 actually. So if you simplify this, then you get 2 cube by 4 by 12, so this is 8 by 12, so 2 by 3, so H2 star is equal to 3 by 2 plus 2/3, so this gives you 6, 9 plus 4, 13 by 6 meters. So that would be the case. Now which tells you from this point you have this H2 star is 13 by 6 meters. Okay, so this is 13 by 6 meters. Now if this is 13 by 6 from the free surface, then what is this depth actually? Can anyone tell me? 13 by 6 minus this half, correct? So 13 by 6 minus half. If you do, we would end up with 13 minus 3, 10 by 6 meters. Okay, so basically if you have this one, the H2 star is acting at a depth of 10 by 6 meters. So then what would be this length? 2 minus 10 by 6, which is 1 by 3 meters. That's all. Okay, so H or this A is equal to 1 by 3 meters, of course. Got it? It's just some geometry, that's all. You know one length, then the other length you should calculate. Is this okay to all of you? So did you all get this? Calculation of this FH2 I have done in an alternative way to make you understand the imaginary fluid column length. That's all. Fine. Yeah. So basically, when the surface at the beginning is not at atmospheric pressure, we will construct a hypothetical column and we will calculate FH and H bar based on these things. Okay. So if you have 1 by 3, if you have 1 by 3, then let's see, therefore A is equal to 1 by 3 meters. So therefore sigma m is equal to 500 into 7 by 3 plus 6000 by into 1 by 3. So into 1 by 3, this whole multiplied with G actually. So you will get sigma m as some Newton meter per 1 meter width. You can convert this to kilonewton meter per meter width of the gate. So 3500 plus 6, this is 6000 and this is 3500. So 9500 divided by 3 into 9.81. So 31065 is what you're getting. Okay, that's the actual value. Clear to all of you? Everyone, Vignesh, mechanical rockstar, Yashwant, Nitish, all of you. The calculation of depth of center of pressure, we should take the value of this H bar from the phase surface actually. That's the only idea. In choosing the B value, we have done some calculation. Let's see. This is correct. So half you'll go. Okay. So then depth of the centroid is 2 plus half. Half plus this is total 2 meters. So 1. So half plus 1 is 3 by 2. Okay. So H bar is 3 by 2. It's okay. So 3 by 2 plus B d cube by 12 into area into H bar. So 3 by 2 plus 2 cube into 2 by 3 into. So 2 gets cancelled. Oh. Then I think we missed this 3. Yes, correct. There is mistake in this. I left this 3 part in the calculations. Okay. Sorry. Thanks for telling Yashwant. I missed this 3. Okay. That 3 also should be there in the calculation. Okay. So let's see. Let me write once again this term. This is the reason why I don't get all India 1. Okay. We keep doing these businesses. 3 by 2 plus Ixx 1 B d cube by 12 into area into H bar. Okay. So if you do this calculation peacefully, 2 gets cancelled. Okay. So then this is 8 by 12. So 2 by 3. So 2 by 9. Okay. So this is 2 by 9. Correct. So this value is 27 plus 4. 31 by 18 meters. Okay. So this is 31 by 18 from this. So if this is 31 by 18, it's not 13 by 6. 31 by 18 meters. Correct. So if you do 31 by 18, then 31 by 18 minus half if you take, so minus half if you subtract it, then from this point this depth of center of pressure is how much? 31 by 18 minus this term. So 36 minus this is 62 minus 18 upon 36. Correct. So 62 minus 18 is 62 minus 18 is actually how much it is? 40. 62 18. Sometimes my mind, you know, this is 44. 44 by 36. 44 by 36. Okay. So 2 minus 44 by 36 is actually this length, which is A. So A is equal to 22, 18, or 4 table you can cancel directly, I think. So this is 11 and this is 9. So 7 by 9 meters. A is 7 by 9 meters. This is not 1 by 3. So 7 by 9. Then this value changes. Is this okay now? It's fine. Now I hope we have done the calculations correctly. Yeah. Just check it. The depth of center of pressure from this point is 31 by 18 is what I'm getting. So obviously if you delete this half, 31 by 18 minus half is 44 by or 11 by 9 generally. So A is, since you are measuring from the base, so 2 minus 11 by 9. So 18 minus 7, yeah, 7 by 9. Let's do this calculation once again. So 3500 by 3, let's do the calculation directly using calculator. So this value plus 42,000 divided by 9. 42,000 divided by 9. So this is the full value into this G. G is 9.8. Okay. So 57166.6. So 57.17 kilonewton meter per meter. That's the value we are getting. Okay. Now is this correct? Everyone. So just confirm. Did you all get this answer? The calculation of H star is crucial in this case. Okay. Rest all are easy parts. Calculating FH1, H1 star. Okay. Then FH2, H2 star. These things are okay. But calculating this is the most important part of the question. H2 star calculation. Okay. H2 star calculation is not very tough. Basically, it's just these 2-3 lines, whatever you do. Okay. So 57.17 kilonewton meter per meter width of the gate. Okay. So this is 57.17. Yeah. I hope all of you understood this H2 star calculation. Okay. So this is hydrostatics which involves here. Yeah. Chalo, let's solve this question. A spherical balloon, again 2014 NAT, which also you can see 2014. So a spherical balloon with a diameter of 10 meters shown in the figure below is used for advertisements. The balloon is filled with helium. Characteristic gas constant of helium is 2.08 kilojoule per kg Kelvin at ambient conditions of 15 degrees Celsius and 200 kilopascals. Assuming no disturbances due to wind means this balloon is tightly floating. Otherwise, what happens? The flowing wind could swing this balloon, but no disturbance due to wind. So it is just held tight. Okay, means there is no drag in the other directions or something. The maximum allowable weight in Newton of the balloon material and the rope required to avoid the fall of the balloon. Okay, so if this balloon has to stand here, then definitely whatever is the weight that you have of this rope, all these things, so this should be balanced by the buoyancy force. Correct? That's what you should have. 5,300 maybe, I don't know. Let's check it up. Okay, so solution. For avoiding the fall of the balloon, this weight of the balloon plus rope should be balanced by the buoyancy forces. Correct? That's what you need. Now, this weight, what they're asking you finally? The weight, the maximum allowable weight. Okay, fine. So directly buoyancy force. So let's say this string has very negligible volume. So the buoyancy on this thread, whatever is there, is very small. So if you take this as the volume on which there is buoyancy, so density of air, atmospheric air, into G into this volume of the balloon actually. Okay. So this is the volume. There is no wind disturbances. It's clearly given, assuming no disturbances due to wind. Okay. So density of air. So they have given the characteristic gas constant for the air at ambient conditions of 15 degrees Celsius and 100 kilopascals. Okay. So then the balloon is also filled at 15 degrees Celsius and at 100 kilopascals. Okay. Helium at these conditions, assuming no disturbance, and this is the density characteristic gas constant. Okay. So how would you get the volume of the balloon? volume of this balloon is almost nothing, but if you neglect the small balloon material thickness, then volume of the balloon is exactly the volume occupied by the helium, correct? Yes or no? So this volume can be written as density of air into G into volume of the balloon, actually, or volume of the helium, let's say, volume of the helium which is inside this balloon. Okay, so if you simplify now, density of the air, they have given the characteristic gas constant, okay, and also they have given the atmospheric conditions, so you can get density which is P ambient by R air into T of this ambient again, okay, because A is at that constant, so G into volume of helium. So again, if you apply the ideal gas equation treating this helium as ideal gas, then what you would get, volume, right? So volume is equal to RT, okay, this is V, M RT is what we need, correct? So just a second, this is in Newton, so we want the volume of the helium. Okay, they have given the direct conditions, no, 10 meters, so pi by this 10 is diameter, so pi d cube by 12, so this is the volume occupied by the helium because they have given the diameter straightforward, so pi into 10 cube by 12, that's all. So we have this situation. So if you simplify this, we would get the answer weight. Okay, so let's see, weight is equal to ambient conditions 100 kilopascals, so 100 into 10 cube kilopascals by characteristic gas constant of air 0.289 is given, so 289 joule per kg Kelvin. T ambient, this is 15 degrees Celsius, so 273 plus 15 is 288.15 into G. So G, nothing is mentioned, so nothing is mentioned, no, so let's take 9.81 into pi d cube by 12, so this gives you the weight in some newtons. So this is the weight in newtons. Air T ambient. Okay, so this is what you get. So if you simplify this value, let's see, this is 10 power 5 by 289 into 288.15. Okay, 289 into 288.15, so 1.2, that's the density of air, of course, into 9.81 into 9.81 into pi into 1000 by 12, so into pi into 1000 divided by 12, so 3084.04, 3084.04 newtons. Okay, so this is what you're getting. You missed 4/3 in the volume of helium, but this is diameter, no, sorry, this is diameter. Okay, so volume is equal to 4/3 pi r cube, so this can be written as 4/3 pi r can be written as d by 2, so d cube by 8, so pi d cube by 6. Acha, okay, this is 6 not 12, sorry, pi d cube by 6, no, so pi d cube by 6, 4/3 pi r cube, so 3 4 2s are 8, so 2, so this is 6, pi d cube by 6, correct, so this should be 6. So if this is 6, then this value is double into 2, 6168, 6168.09, so 1 newtons. This should be the answer. Okay, so that should be the weight of the balloon and this said whatever conditions, so that this balloon will float in the air. Okay, come on guys, type in the chat box, is this okay to all of you? Deepak, did you understand this conversion? Yeah, I misjudged it because I was in this. Answer key is different, but why? This weight should be balanced with this buoyancy, right? (6171.3), 6171, 6168.1 is what we are getting. What is there in the key? 61. G is not given, right? So we can take 9.81 if nothing is given. 6168.09. Yeah, of course, 6168.1, whatever. And what is the key given? Because as per my idea, this should be the case. Weight and buoyancy should balance because there is no other forces. 5300 to 5330. 5315 is what you should get. But how come? Spherical balloon with a diameter of 10 mm. Correct. So that's the volume is filled. Okay, see, got it. This is, let's read the question carefully. Okay, the weight in Newton of the balloon material and the rope. Okay, which means, but this is weight of balloon material plus rope plus weight of helium inside this. Correct? Did you understand this? Did you get whatever the calculation we have done? This is the weight of this balloon material plus the helium inside and the rope weight actually. But they are asking you the weight of only the balloon material and the rope. So then what we have to do? Ultimately we have to subtract this weight of the helium from this answer. Okay. So let's do that. So therefore weight of balloon material plus weight of rope is equal to this W minus weight of the helium. So how do you get the weight of the helium? Mass of the helium into G, and mass of the helium can be written as P into volume occupied by the helium by R times R of the helium into T ambient, and this is at P ambient because the helium is also filled at the same conditions, into G. So this is what you need. Chalo, let's see. 100 into 10 cube into volume occupied by helium, just now we have calculated, no, something, 1000 pi by 6 by characteristic gas constant of the helium is how much? This guy 2.08, so that's in kilojoule per kg Kelvin. Okay, so 2080 into ambient 288.15, right? That's what we have taken now, 288.15 into G 9.81, whatever. So this is weight of the helium. So this would also be in some newtons. So therefore, you know this weight of balloon material plus weight of the rope actually. So if you do this, you will get the answer in some newtons. That's all. So let's make this calculation. 2, 3, 5, 5 plus 3, 8. So pi into 10 power 8. Okay, so this is the value divided by 2080 into 288.15 into 6. Okay, into 6. So this value into 9.81. So 857, almost 857 newtons. Okay, and what is this value? We got 6168.1. So subtract this. Okay, subtract this from 61. What is the value here? 6168.1. Okay, so 6168.1, 5311.1. That's all. Okay, so this is the correct answer. Clear to all of you? So they want only the balloon film material weight and also the rope weight. They don't want the helium weight inside the balloon. That's the question given. Okay, yeah, 5310, 5311, whatever. It's very close. Fine. So we should read the questions carefully. Next question onwards, I'll be more attentive in reading the questions. They have asked only the balloon material plus this rope weight. Okay. Fine to all of you. Did you all understand this question? It's clear? Everyone, type in the chat box. Is this okay? Let me have some water meanwhile. So we should be careful. Okay. Next, to solve this question, 2020 MCQ. Which of the following conditions is used to determine the stable equilibrium of all partially submerged floating bodies? Come on, answer this question. I'll give you a moment. Center of buoyancy must be above center of gravity. Center of buoyancy must be below center of gravity. It is floating body. Okay, floating bodies, partially submerged floating bodies. Meta center must be at a higher level than the center of gravity. Meta center must be at a lower level than the center of gravity. Come on, answer this. What would be the answer? It's a partially submerged floating body. सोल्यूशन वाली स्लाइड देखना है, ठीक है? Okay, it's a straight thing. So basically, for partially submerged floating bodies, meta center must be at a higher. Okay, so for partially submerged body, submerged floating body to be in stable equilibrium, to be in stable equilibrium, M lies above G. Okay, and normally in case of completely submerged bodies, your center of buoyancy should lie above G, of course. Okay, so C is the correct answer. Of course, 2014 for a completely submerged body with center of gravity G and center of buoyancy B. So just now we have seen this should lie, G is located above B, G is located below B, G and B are coinciding independent of the location of G and B. So it's a completely submerged body, so clearly G is located below B, of course. Okay, so you know, for completely submerged, sometimes we look like these questions are very easy, why to solve this again, but you see they are coming in GATE exam. Okay, so for completely submerged body, G lies below the center of buoyancy. Okay, so G should lie below the center of buoyancy. A very straightforward question. Chalo, let's see. A flat plate of width L is equal to 1 meter. So this is the width, L is equal to 1 meter, is pushed down with a velocity U is equal to 0.01 meters per second towards a wall, resulting in the drainage of the fluid between the plate and the wall. So obviously, if you are pushing this plate from this edge, the plate is the fluid is moving. Okay, assume 2D incompressible flow and that the plate remains parallel to the wall. So the plate is remaining parallel to the wall. It's a flat plate. Okay, so it's a flat plate and this is remaining parallel to the wall. The average velocity of the fluid film draining out at the instant shown in the figure. Correct to 3 decimal places. Okay, if you are lucky, we will get that question, sir. Maybe. Okay, so let's see the case here. This is a plate and this plate is coming down at a velocity U. Now imagine you have a open fluid. If you put a flat plate on that and if you try to press the plate, then definitely from the sides the fluid will come out. Correct? Yes or no? So can you all understand that this U average is here? Yes or no? Is this clear to all of you? Now let W be the width of the plate. Okay, let W be the width of the plate. Okay, from mass conservation, this is a flat plate. Okay, no diameters, nothing, there is a small gap. Whatever the rate at which this fluid comes up, the rate of change of volume inside this is nothing but, or if you take this as a control volume, for example, okay, then if your plate is coming in this way, the fluid is going out. Okay, so can I say this as m dot in minus m dot out is equal to rate of change of fluid inside the control volume. Okay, then this m dot in is 0 because you see practically into that volume no fluid is going. Okay, then minus m dot out is nothing but So minus density of the fluid into area. So if this is of width W, this area here is d into W for the fluid flow. Here also d into W for the fluid flow actually. Okay. So and clearly it's given, assume 2D incompressible flow, that the plate remains parallel to the wall. The U average of the fluid draining out at the instant shown in the figure. Okay. But this plate has a width W. The fluid is moving only in this direction, so it's completely moving, right? So you can see the area, the U average is uniform at all the points, and let's say fluid is moving out in all the 4 directions. Then just a second guys, let's read the question once again carefully. Flat plate of width L is equal to 1 meter. So there is a flat plate of width L is equal to 1 meter. So this is L, they have given this is L here in the question. Okay, L is equal to 1 meter is pushed down towards a wall, resulting in the drainage of the flow. Assuming 2D incompressible flow and that the plate remains parallel to the wall always, then U average of the fluid draining out at the instant is, so rho F into the area of outflow is d into W and d into W. So 2 times d into W into U average is equal to d by dt of mass of fluid inside the control volume is density of the fluid into volume. Okay, so what is the volume at any given instant? D L into W. So d into L into W. Okay, now let's see if you take the dimensions of the plate common. So L is 1 meter anyhow. So if you cancel this width W, actually density of the flow and density of the fluid is also constant, you can bring it out. So this gives you minus 2 times D. So what is D? 0.1 at this case into U average is equal to D times D by dt, means this gives you the rate of change of this dimension with the time. Now imagine if this plate is coming down with a velocity u, then the rate of change of this d is nothing but this minus u, correct? Because d decreases with time. So this is minus u, of course. So u average is equal to u divided by 0.2. So what is this value? The velocity at which this is coming is 0.01 by 0.2, so 0.5 meters per second. So that's the average velocity. Okay, so it should be 0.5 to 0.01 by 0.2. It should be 0.5, sorry, 0.05 now. Let's see, 10 power minus 2 by 2 into 10 power minus 1. So 0.1 by 2, so 0.05, sorry. Yeah, correct, 0.05. Yeah, this value is 0.05. Okay, so you can see this is basically the change. Yeah, 0.05, of course, because this by this is 0.05 actually. Okay, so the rate of change of this dimension d with the time is given as the velocity of the plate at which it's coming. But of course this d is negative, this rate is negative, because as time increases d decreases. Okay, so that's how you have u average as 0.05. Okay, so is this question clear to all of you? Fine. So shall we move to the next question? So this is 0.05. It's a straight answer. Okay, so let's see, let's go to the next question quickly. Fire 2D, it's in 2021, MCQ 2021 actually. So fire 2D incompressible flow having velocity components u and v respectively. This expression can be simplified to a very straight thing again. So firstly, it's a incompressible flow, 2D incompressible flow. So let's see, given flow is incompressible flow. So this implies divergence of velocity is equal to 0. So dou u by dou x plus dou v by dou y is equal to 0. Okay, now let's see, consider dou u square by dou x plus dou by dou y of uv. So if you simplify this, this is 2u times dou v by dou x plus apply chain rule u into dou v by dou x dou v by dou y plus v into dou u by dou y. Okay, so out of this 2u dou v by dou x, we'll write it separately. So this can be written as u into dou v by dou x plus u into dou v by dou x plus u into dou v by dou y plus v into dou u by dou y. That's what you get. Okay, so then clearly this summation is 0. This is equal to u times divergence of velocity, so which is equal to 0. Okay, so you have u dou v by dou x plus v into dou v by dou y. That's all. Sorry, plus u into dou v by dou x plus v into dou u by dou y. Option D, right? This option, no? U into dou v by dou x plus v into dou u by dou y. Right? So option D is the correct answer. So this gives you u dou u by dou x plus v dou u by dou y. Okay, so which is in option D. Okay, it should be D. Fine. So next, let's go to another question. Consider it's a 2017 MCQ, the time when I have written gate for the first time. Solution. Consider the 2D velocity field which is given by this. So given x component of velocity is 5 plus a1x plus b1y, because this is the coefficient of I and this is the coefficient of j. So v is equal to 4 plus a2x plus b2y. Okay, a1, b1, a2, b2 are constants. Which of the following conditions needs to be satisfied to the flow to be incompressible? Okay, so now we know for flow to be incompressible, dou u by dou x plus dou v by dou y has to be 0 clearly. So this gives you dou u by dou x is a1, dou v by dou y is b2 is equal to 0. So a1 plus b2 is 0. That's all. Okay, so this question is actually directly available in Munson book also. Chemical engineering भी तो देख सकते हैं क्या? You can generally see Soham. It's okay, fine, because you'll get general idea in how to solve the questions. Okay, so this is B, of course. So a1 plus b2 is equal to 0. A very tight 1 mark question maybe. So let's see 14th question. Then 2016 MCQ. For a 2D flow, the velocity field is given by v is equal to x by x square plus y square I plus y by x square plus y square j, where ij are the basic vectors in the Cartesian coordinate system. Identify the correct statements. Flow is incompressible, flow is unsteady, y component of acceleration, x component of acceleration. Okay, so curl we na, they asked incompressible, no? If they asked irrotational, then curl. Okay, because omega is equal to half curl v. So if omega is angular velocity vector and if omega is 0, then curl v is also 0 actually in that case. Okay, but right now we're talking about the incompressible effects. You remember the continuity equation I have told you, dou by dou t plus divergence of rho v, or this is same as this total derivative of density plus rho times divergence of v. So divergence of v is 0. Okay, so let's see in this case which of the following statements are correct. So let's write the velocity profile first. Solution. Given the velocity field is equal to x by x square plus y square I cap plus y by x square plus y square j cap actually. Okay, now what are the points of interest? First, flow is incompressible, flow is unsteady, y component of acceleration, x component of acceleration. Okay, so let's see, u is equal to x by x square plus y square, v is y by x square plus y square. This implies u is not a function of time, v is also not a function of time. So clearly this flow is unsteady is correct option. Okay, sorry, this is the wrong option because there is no involvement of time, so flow is steady. So wherever there is 2, eliminate those statements. A and C are wrong options. Okay, then these days everything is mixing up. Yeah, of course. Because of that compressible flows, I understand. Fine. So now let's look at incompressibility and also this guy AY and AX. Okay, if you check incompressibility, that's done, because if you have flow as incompressible, then option 1 is correct. Here there is no option 1, so B is the answer. Or if flow is compressible, means if divergence is not 0, then this is wrong, this is the correct answer. Okay, so let's check it. Checking incompressibility of the flow. So divergence of V, dou U by dou X plus dou V by dou Y. So which gives you dou U by dou X. So if you differentiate this with respect to X, X square plus Y square into partial derivative of X is 1 minus X into 2X by X square plus Y square whole square. Okay, plus dou V by dou Y, similarly here X square plus Y square into 1 minus Y into 2Y by X square plus Y square whole square. This is the differentiation. So this gives you divergence of this velocity field is, this is Y square minus X square, this is X square minus Y square. So both will get cancelled. So this is 0. So this tells you flow is incompressible. Flow is incompressible. So this first statement is a correct statement. So but 1 is not there here. They were asking you correct statements. So this is wrong and this is correct option. Okay, X component of Y component of acceleration and X component of acceleration. So how do you calculate this X and Y components of accelerations? Like, you know, AX dou E by dou T, U into dou E by dou X plus V into dou E by dou Y. Okay, so in fact to calculate this you need some time, but in exam the options are very beautifully set, so that, yeah, obviously it will be on the YouTube. Okay, Asit, see, in this question was very beautifully set. Normally to calculate the acceleration you need some time. Okay, basically you need some time to do the calculations and all, but without necessity of doing those calculations, you can figure out this by just checking the incompressibility and eliminating the options. Okay, so anyway, if you do this, I'll just show you maybe for X component of acceleration, you can see it for Y by yourself. Okay, U, which is this, into dou U by dou X. Okay, so if you differentiate this function dou U by dou X, you'll have Y square minus X square, X square plus Y square whole square. Okay, so this is what we have, plus V into V is, what is V? Y by X square plus Y square into dou U by dou Y. So dou U by dou Y, if you differentiate this with respect to Y, X is constant minus X square plus Y square whole square, differentiating, right? So into 2Y, that's all. So this is xy square minus x cube plus minus 2xy square. So xy square minus 2xy square will simplify to some extent, and you will get this something different expressions. Okay, but anyway, B is the correct answer in this question. Okay, but no need to calculate the accelerations for those complicated velocity. It's not complicated but very straightforward. So can you repeat how you got acceleration? I was calculating actually. Okay, this is the expression for acceleration, you know this. Okay, then the U, there is no involvement of time, so the local or the temporal term will go to 0. Now getting to the convective part, U into dou E by dou X, this is U, straightforward. Dou E by dou X we have already calculated here, so x square plus y square minus 2x square gives you y square minus x square by this term. Okay, plus V into, so V is this component, into dou U by dou Y. So when you differentiate this with respect to Y partially, this x is constant, so this is something like the form derivative of some constant k into 1 by a square plus x square. So what do you do this? Minus 1 by a square plus x square whole square into 2x. Okay, so something like that. So if you simplify, xy square minus 2xy square, so we have minus xy square, and this is x cube, so x into y square minus x square, sorry, minus x into x square plus y square by x square plus y square into this. So it just gives you minus xy. That's the acceleration. Okay, just partial differentiation and simplifications. That's all. Okay. So is this clear to all of you? So let's see the next question. Of course, a matching straightforward question. So match the following pairs: incompressible continuity, steady flow, rotational, zero acceleration of fluid particle. Okay. So let's see what would be the matching. So first, curl of V equal to 0 is nothing but irrotational flow field. Correct? Why? Because you see omega is equal to half times this curl of the angular velocity vector. Sorry, the linear this velocity vector. Okay. So if this has to be 0, then ultimately you get divergence of V is equal to 0. Okay. This is for irrotationality. Then so P should go to 3 actually. So here P is going to 4, this is wrong. P is going to 4, this is wrong. Then these two options go, P tends to 3. Then in both Q tends to 1, so there is no point of checking Q. Then R, dV by dt is equal to 0. This is the total derivative. Okay. So if this dV by dt is the full acceleration, so this gives you 0 acceleration of the fluid particle. Correct? Because A is equal to dV upon dt, which gives you dou V by dou t plus V dot del operating on the velocity vector. Okay, so V dot del operating on the velocity vector. So if you have that as the acceleration, then the full acceleration is 0. So R should go to 4. So R is going to 2 in this case. That's wrong. So R is going to 4 clearly. Yes, this is steady state. So this is steady state actually here, and incompressible flow, obviously Q should go to 1. So Q should go to 1. A very simple thing. But these are the conditions which one should know to, because some of you told no, you are getting confused. To avoid those confusions, you should have this. So let's solve this. Consider a velocity field. It's again a question from 2014. Consider a velocity field V is equal to, okay, V is equal to K times Y I cap plus X K cap, where K is a constant. The vorticity about the Z axis is dash. Okay, I just have one question. This is xk cap or xj cap? K is it? So let's see. Solution. Given V is equal to K times yi plus xk. Can somebody tell me this is K or J? It's K. K is what you have in the question. Yeah, 2014. It's right. Okay, then let's solve. So this can be written as ky I cap plus 0 j cap plus kx k cap. Okay, so this implies the vorticity vector is 2 times of angular velocity, which is curl of V. So this gives you I j k dou by dou x dou by dou y dou by dou z ky 0 kx. Okay, now you want the kth component. Okay, vorticity about this z axis. So this is obviously equal to omega x I cap plus omega y j cap plus omega z k cap. Okay, so omega z k cap. This is what you know. Now rather than doing the full determinant simplification, ultimately this omega z is nothing but determinant of dou by dou x dou by dou y ky 0. Okay, so this is 0 minus k, so which is minus k. Okay, that's the answer. So minus k, because you know, if two vectors are equal, the corresponding components must be same. So this omega z is nothing but this 2 by 2 determinant. Okay, and that's what you simplify. Okay, so minus k is the actual answer. So let's see. the velocity field again from 2024, like last year, I mean this year. So the velocity field of a 2D incompressible, two-dimensional incompressible flow is given by V is equal to 2 sine hyperbolic x plus V, where I and j denote the unit vectors. If V of x comma 0 is equal to cos hx, then V of 0 comma minus 1 is dash. Okay, so this is the hyperbolic functions which are known to you. So let's see solution and options are like 1, 2, 3, 4. Okay, so given V is equal to 2 sine hyperbolic x plus V times of x comma y, of course. Okay, now let's see, this can be written as, so all of us know, like okay, let's simplify this directly. So incompressible flow field, so this flow field is incompressible. This flow field is incompressible. Okay, so if this flow field is incompressible, this implies dou u by dou x plus dou v by dou y is equal to 0. So which gives you dou u by dou x. So you have u, let's write the components. U is 2 sine hx, v we don't know as of now, but expectation is since this flow field is 2D, so that can be function of both x and y. Okay, that's what you know in generalization. So dou u by dou x, if you differentiate this with respect to x, 2 into derivative of sine hyperbolic function is cos hyperbolic function plus dou v by dou y is equal to 0. So dou v by dou y is equal to minus 2 cos hyperbolic x. Then if you solve this question, differential equation, v is equal to minus 2 times y into cos hyperbolic x plus some function of x actually here. Okay, because we are integrating partially with respect to y. Now let's see, we know something. To get that function, they have given you one boundary condition. So given v of x comma 0 is equal to cos hx, correct? So which means if you put v of x comma 0 in this case, v of x comma 0, so if you put y equal to 0, this term goes, so this is cos hx, which implies your f of x function is cos hx. Okay, that's all. It's a simple mathematical question, that too based on the simple partial differential equations. Okay, so this is cos hyperbolic x is the function. Okay, so if you write this velocity profile, therefore v of x comma y is equal to 1 minus 2y times cos hyperbolic x. That's the velocity component finally. Okay, so if you do partial differentiation with respect to x, y, whatever, you'll get this answer. So therefore v of, now what is the velocity they are asking you? 0 comma minus 1. So cos h0 is 1, so this is 3. That's all. Okay, one small doubt in previous question. In previous question, that minus 2 cancelled. How that minus 2 cancelled? Where? In previous question, this one. This is vorticity, okay, which is 2 times of angular velocity. So omega is half curl v. Okay, so 2 and half gets cancelled. So 2 omega is only curl v. Then equated. Okay, is this clear to all of you? Angular velocity is only half times of curl, we know, but vorticity is 2 times of omega, so 2 gets cancelled. That's all. Yeah. So if to some of you who don't know what is this cos functions and sin h functions, of course maybe it could be possible. I just want to give you some information. These are the functions. Okay, so in case if you're not very comfortable with writing derivative of sin hx is cos hx, these kind of things, you can just convert this as this part would become e power x plus e power minus x, sorry, e power x minus e power minus x. Then you differentiate, you can get the things like this. Okay, so 3 is the correct answer in this case. A very small simple question, okay, just based on simple maths, very cute and little maths. So let's see 2018 MCQ. For a 2D incompressible flow field given by this, where A is positive, so this A is a positive constant, which of the following statements is false? Okay, it's a MCQ, so single option. First, what are the things? Satisfies continuity equation, unidirectional when x tends to 0 and y tends to infinity. Its stream lines are given by x is equal to y. It is irrotational. Okay, so let's check what are the cases. Given u is equal to ax and v is equal to minus ay, because that's the velocity profile. Okay, u is equal to whatever the velocity vector is, ux plus ui plus vj. Okay, so first checking continuity equation. Okay, no involvement of time, so if you write d rho by dt, or you can write maybe like continuity equation, dou by dou t. Okay, it's directly given, it's incompressible flow field. Okay, so incompressible flow field and it's 2D, which means this u and this u, there is involvement of both x and y in the profiles. Okay, so then dou u by dou x plus dou v by dou y is the continuity, so is equal to dou u by dou x a plus dou v by dou y minus a is equal to 0. So this velocity profile satisfies the continuity equation. So this statement is correct statement, so you cannot choose this because they are asking you for the false statements. Okay, then second, it becomes unidirectional when x tends to 0 and y tends to infinity. This is also correct because as x tends to 0, you have only u is equal to minus ay j cap, and it's only depending on y, so it is 1D flow. So you have only involvement of only one variable in the velocity vector, so clearly it's 1D flow. Okay, then case 3, so this is also a correct choice, so this is also a wrong statement. Then third, what about the third one? Third one tells you the streamline equation. So streamline, since it's u and v are known to you, dx by ax is equal to dy by ay. Okay, so a and this a gets cancelled, so upon integration you'll have ln x is equal to ln y plus constant. So this implies x by y is equal to some constant. Okay, so x by y is equal to some constant. Let's also calculate the fourth statement. It is irrotational. So if you see, u is equal to ax, v is equal to minus ay, so dou u by if you have irrotationality, so let's check it. Normally the angular velocity vector is half into dou u by dou y minus dou v by dou x. This is about the z axis. So dou u by dou y is 0 and dou v by dou x is also 0. Okay, so this is irrotational, which is false. So let's see, looks like all four are correct. Continuity equation, it's satisfying. As x is tending to 0, it becomes unidirectional when x tends to 0. So if x tends to 0, there is no this component, you have only y component. Okay, then C, its streamlines are given by x is equal to y, but not all the streamlines. Okay, so some streamlines can be x equal to 2y, x equal to 3y. Only one of the streamline is of this form. It is irrotational, so clearly this is 0, so omega is 0. So irrotational flow field. Okay, so this is irrotational flow field, so definitely we can go with C. Okay, because not like this is also correct, so we cannot choose. Its streamlines are given by x is equal to y, not all the streamlines. This is the correct choice because not all streamlines are x equal to y. Okay, okay, here there is a minus sign, then it's xy is equal to constant. Okay, yeah, because this minus sign is missing. Correct. If you put minus here, then this becomes minus. So log x plus log y, ln of xy is equal to constant. Okay, so xy is equal to constant. That's the streamline equation. So C is the correct option, of course. So let's see. Consider a flow through a nozzle as shown in the figure. Okay, so there's a nozzle basically as shown in the figure. The air flow is steady, incompressible, and inviscid. The density of air is 1.23 kg per meter cube. Pressure difference P1 minus P atm is dash kilopascals. Okay, so there is a flow through the nozzle, of course. Then what they are asking, the pressure difference P1 minus P atm. Let us apply the Bernoulli's equation maybe. So if you apply this Bernoulli's equation at this point and also at this point, so let's call this point 1 and point 2. Then solution. Applying Bernoulli's equation at points 1 and 2, at points 1 and 2, this implies P1 by OG plus V1 square by 2Z plus Z1 is equal to P2 by OG plus V2 square by 2Z plus Z2. Okay, and this is a horizontal nozzle, so clearly no effect of the potential heads. Then here V1 is not given. Okay, and V2 is given, A2 is also given, A2 is given. Just a second guys, A1 and A2, I think there is some small catch. In this cases they typed the same values. A1 is 0.2 meter square and A2 also they have typed 0.2 meters square. Can someone tell me this is correct or this is correct? I think this should be short or maybe this should be big. Just look at the question and tell me once. Madhuji or Pratim Nath. One is 0.02. Which one? This one or this one? This is 0.02. The second one. Good Prasanjit. So tell me. Because here in typing I think they have done the mistake. A1 and A2 both they have given the same, but definitely A2 would be small. A2 0.02. Okay. It's fine now. Clear? Chalo. If this is fine, then the density of air is 1.2 kg per meter cube. Steady, incompressible. So it's incompressible flow field. So we can take the density to be uniform all over. So P1 minus P2. So let's see. You can apply the continuity equation. So for A1 V1 is equal to A2 V2 since flow is incompressible. So this A2 is 10 times. Okay, I mean A1 is 10 times of A2. So V1 is V2 by 10, which is V1 is V2 by 10, which is 50 by 10. So 5 meters per second. meters per second is the flow velocity at this point. Okay, same 𝐶 के लिए होगा ना sir? Yeah, definitely it happens. So let's see. In this case, P1 minus P atm. So this is P1 and P2. This nozzle is discharging to atmosphere. You can see. So P2 is P atm. So P1 minus P atm is equal to rho times of V2 square minus V1 square by 2. And if you calculate this value, you will get in pascals. They are asking in kilopascals. Okay, so 1.23 times V2 is 50. Okay, so V2 is 50. 50 square minus 5 square by 2. So this would be in pascals. So which means you can get this P1 minus P atm in some kilopascals. Okay, this should be in some kilopascals. So let's see. 50 square minus 5 square by 2. 50 square minus 5 square by 2 into 1.23. Okay, 1522125. 0.125. So in kilopascals 1.522 kilopascals is the pressure difference in the between the inlet and exit of the nozzle. Simple Bernoulli equation and continuity can give the answers. Okay, clear? So 1.522 is the actual answer. Let's solve this. A 2D incompressible flow field, 2019 question. A 2D incompressible flow field, frictionless flow field, is given by V equal to Xi minus Vj. If rho is the density of the fluid, expression for pressure gradient vector at any point in the flow field is given as. Okay, so let's see solution. We want pressure gradient, so let us go with the momentum equation. Okay, so it's incompressible flow. So for incompressible flow, you know, rho x bar body force per unit mass minus gradient of P plus mu times del square V is equal to rho times dV upon dt. Okay, so this is the Navier-Stokes equation for the incompressible flows. Okay, if you want for compressible flows, here you have one more component plus lambda, second coefficient of viscosity, times gradient of divergence of velocity. Okay, you can write for any flow in general using Stokes hypothesis. Okay, for any general flow, the actual Navier-Stokes equation is plus second coefficient of viscosity times gradient of divergence of V is equal to rho times dV upon dt. Okay, so that's what you get. And normally you see sometimes this lambda is minus 2/3 times mu, but normally within the compressible flow regime that minus 2/3 mu is not very well valid. Okay, the experimental results are not very satisfactory, so just people leave this as lambda. So let's write the words 2D. Okay, we don't bother. Incompressible frictionless no viscosity is given by Xi minus Yj. Rho is the density, expression for pressure gradient. Nothing is mentioned about the body force, so let's take it to be 0. Okay, so this gives you gradient of P is minus rho times of dV by dt. Okay, which means rho times the acceleration vector. So this can be written as minus rho times of Ax I cap plus Ay j cap. So let's see what is Ax. The acceleration in the x direction is dou E by dou t plus it's 2D, so you can just write these expressions. Okay, so plus V into dou E by dou y. So let's look at the velocity profiles. U is x, V is minus y. Okay, so V is minus y. That's all. No involvement of time. Dou E by dou x, dou E by dou U by dou y. There is no involvement of y here. So this gives you U into dou U by dou x, which is 1. So this is the x component of acceleration. Similarly, what about Ay? Ay is equal to dou V by dou t plus U dou V by dou x plus V dou V by dou y. So if you simplify this, again there is nothing here and V doesn't have x, so this term is 0. So V into dou V by dou y, which is minus 1. So this is y actually here. Okay, so that's all. So this tells you that gradient of P is equal to minus rho times of Ax is Xi plus Yj. That's all. Okay, so this is the expression for the pressure gradient in this case. Okay, so minus density times of Xi plus Yj, so which is in option B here. Okay, so B is the correct answer. So that's the correct option because of this simple analysis. Normally this is the Navier-Stokes equation for any flow, and this lambda is the second coefficient of viscosity. Okay, sometimes what people do is they write lambda is equal to, guys, sorry, here it should be lambda plus mu. Yeah, it should be lambda plus mu. Please correct it. This should be lambda plus mu. So many PSUs are keeping 65% as cutoff. I have final CGPA of 6.54. According to college conversion, it is 60%. Could you please tell, will there be other chances for me? Definitely, Siddhartha. I'll tell you one thing. So normally anyone who has these issues with CGPA or percentage, many PSUs they put 65, but there are plenty PSUs which put only 60%, or sometimes they even go for 55%. Okay, so 65 is also very often. Normally in ISR case it's 6.84 should be the CGPA minimum. Okay, so that's why if you are in second year, or I mean definitely in this session there would be very few people of second year, third year, but please focus on your CGPA at least in the some part. Make sure it's above 7.5 so that nobody put any hold on you. Okay. Fine. You have options, don't worry. There are PSUs which asks you for 55%, 60% and all, but as you have seen, many ask for 65%. Okay, but don't worry, you can top it up. If not, you can do one thing else. You have passed out. Okay, so better write GATE and go for an MTech, get some good CGPA in the masters, you'll get placed, and then you can apply for other organizations as well. Okay. When I was telling about this percentage, someone has asked me what is my BTech percentage, what is my MTech percentage and all. Okay, so but anyway, I'm telling that, see, during college time many of you feel that it's okay, you know, roaming in the campus with one button unhooked, these things are the biggest things. No, these are very, you know, the things which can keep people low, but later by the time you realize you'll finish everything. Okay, so normally if you have your juniors or someone, at least make them believe that something around 75% is minimum. Okay, above it it's good. Obviously you have every option, every door open for you. Okay, CGPA do matters sometimes. Yeah, chalo, let's see. Let's go to the next question. This fellow, a 60 mm diameter water jet strikes a plate containing a hole of 40 mm. This is a direct question from Parakram. It has given in GATE examination. You are the first bencher student or back bencher student? Many of the times I used to bunk the classes, so no bench. I used to only in the canteen benches. But at some points in my life I used to sit at back bench, but since I was performing very low during childhood, teachers used to bring me back to the first bench. Okay, it happened. Many times you see, when I was in schooling, no, my maths was very weak. Like till 4th class I remember I have done very well, but 5th, 6th, 7th, my education was completely low. Okay, I used to sit in the somewhere in the class and just enjoy my life. Okay, but then, you know, obviously things happen which can change you. Even in 7th class, you know, 7th class, imagine 7th class, like where, you know, already algebra 5th class and all is finished. If this is there, I know writing this. Okay, in 7th I'm talking about 7th class, but if this is given, I don't know how to write this. Okay, honestly speaking, I still remember my 7th class maths teacher told me in front of the complete class, you know, it's a real thing that happened. Okay, I'm not bluffing or anything. If you want, you can come to my college and you can ask. The same teacher is still working. He became old now a bit. So he told me, like, Vinay, you won't even pass 10th class. I'll write it on a signed paper and will give you. You can keep it. This is the statement he told in front of the complete class. Okay, it's nothing wrong from his side also, because my performance was at that extreme levels, so that made me tell this statement. Okay, but later eventually things happen in life and you keep changing. Okay, and now at least I'm good enough to teach GATE maths. Okay, and some maths beyond that as well, in fact. Okay, so that's why I always believe in one thing: it's never late to start anything again. Okay, so let's say till today you don't have knowledge, but it's okay. A point is not known to you only until you unlearn it. Okay, or basically you don't know it. Okay, clear? So just keep focused, keep studying, and move on. So let's see, in this case, solution. A 60 mm diameter water jet strikes a plate containing a hole of 40 mm, okay, of 4 centimeters, as shown in the figure. Part of the jet passes through the hole horizontally and the remaining is deflected vertically. Okay, so this part of the jet, this directly passes through this. Okay, there is no momentum change for that fluid. Now whatever is the remaining volume of the fluid, this is undergoing some change. Okay, so this part is undergoing some change basically. If this part is undergoing some change in momentum, then the force acting on the plate is only because of this part of the fluid which I am hatching. Okay, so therefore from Reynolds transport theorem, from RTT, sigma F on plate is equal to summation m dot v at the inlet in the x direction minus summation m dot v in the x direction at the outlet. Okay, so clearly the mass which is equivalent to this hatched portion is only undergoing momentum change. Okay, this mass which is inside this core is not undergoing any change. Okay, so this is 20 meters per second, and obviously this is also 20 meters per second. So if you see, Fx on plate is equal to, since whatever the mass is in the hatched portion, same would be the mass in this deflected part. Okay, so if you take m common, so rho into pi by 4 outer diameter square minus inner diameter square. So outer dia is 60 mm, 6 centimeters, and this is 0.04. So 6 square minus 0.04 square. So this is the mass which is being deflected. Okay, so then are you from SRK? Yes, I am from SRK mechanical. Okay, so rho into pi by 4 into 0.06 square minus 0.04 square into, at the inlet you have the x component of velocity in this direction which is 20 meters per second. At outlet, nothing in the x direction. Okay, so 20 minus 0, that's all. So if you simplify this, it's water jet obviously. So density into pi by 4 times this value 0.06 square minus 0.04 square. So 0.02 into 0.1 into 20. That's all. Okay, so you can just do the simplification. So this 10 cube and this will give you 2, 10 pi, so 31.41 newtons. Yeah, 628.318. Did I miss something? So yeah, square should be there, into 20 should be there, correct, because mass is density into volume into, density into area into velocity. So into 20, so you should have 20 here. So if you have 20, 628.2, correct, because mass flow rate is density into area into velocity into change in velocities. Yeah, into 20 should be there, correct. So 628.2 or 628.3, whatever. Okay, so it's basically 200 times of pi, 200 times this pi, 628.31. Okay, okay, 628.318 newtons. So that's the force that you get. Fine, so let's solve this question. 2021 again. Water flows out from a large tank of cross-sectional area AT is equal to 1 meter square. Okay, so this is A1, I think. Okay, A1 is equal to 1 meter square to a small rounded orifice of cross-section A0. So there is a A0 actually located at y equal to 0. Initially water level H measured from y equal to 0 is 1 meter. So this is 1 meter. Acceleration due to gravity is 9.8 meters per second square. Neglecting any losses, the time taken by the water in the tank to reach a level of y is equal to h by 4. Okay, please resend slide once. Yeah, so if you do MTech and good CGPA, then the companies will only ask for MTech CGPA. Yeah, generally they ask you only for MTech. Many times even they have constraint in BTech CGPA for a few companies, but that won't get affected much once you have this MTech degree. Okay, okay, Mahavir. So let's solve this. So if you take this control volume again, so if you take this control volume, okay, at y equal to 0. Maybe this diagram was slightly given like this in gate exam. So in this control volume, applying mass balance, you know, m dot in minus m dot out is equal to rate of change of mass of the control volume, okay, mass inside the control volume. So clearly there is no mass which is inflow, so mass to outflow minus density of the fluid into this flow is to area A naught, so A naught into the velocity. So what is the velocity at this point? So some velocity v, so v is equal to d by dt of mass inside the control volume, so density of the fluid into this area of cross section of this tank is A1, so A1 times h, which is the instantaneous height of the water level inside the tank, okay. So let's see, then again this flow is incompressible and all, you can cancel these densities whatever. So can I say by Bernoulli's equation at points 1 and 2, okay. So if you have this as point 1 and this as point 2, of course, okay, so this as point 1 and this is point 2. In fact, you can see this A1 is very greater than A naught, okay. Like you see, A1 is equal to, if you convert this to centimeters, 10 power 4 centimeters square, and A naught is only 1 centimeter square, which tells you this velocity whichever is coming, I can neglect this, okay, because you see this A1 is very large, the tank is very big compared, it's almost like 1000 times of this, sorry, 10,000 times of that cross section. So we can neglect the velocity at which this level comes down, okay. So if you apply this Bernoulli's equation, it is open tank, and here also this is open to atmosphere, so P1 by ρg plus V1 square by 2g plus Z1 is equal to P2 by ρg plus V2 square by 2g plus Z2 actually, okay. Then clearly this P1 and P2 are same because both are open to atmosphere. Then this V1 is very small because the area of the tank is very big compared to the orifice. Then if you take Z at 2 as 0, or let's keep it for some time, you will understand this, okay. So this gives you V2 square by 2g is equal to Z1 minus Z2. So what is Z1 minus Z2? This is capital H, the height at any given instant in the water tank. So V2 is going to be, or which is V, which we have generalized, so this is root 2g h, okay. So let us substitute all these things in this mass balance equation, okay. So if you substitute in the mass balance equation, so this implies minus A naught root 2g h is equal to A1 can be taken out as constants into dh upon dt, okay. So it's a single differential equation, and we also have the you know, boundary condition, okay. At t equal to 0, this h is capital H. Then at t, some value of t, the value of h should be h by 4. The water should fall to h by 4 level, correct? That's what it's given. Neglecting any losses, the time taken by the water in the tank to reach a level of y equal to h by 4, okay. So this can be, it's a simple differential equation, we can solve this. So let's solve this. Minus A naught by A1 into root 2g into dt is equal to 1 by square root of h dh, correct? This is what you have. Now let's, we know the initial conditions and all, let's substitute. At time t equal to 0, the height is h. At time t, we don't know what is the time, this height should be h by 4, okay. So it should, else let me just write it as h to h by 4, because h equal to h by 4 looks very confusing. So at time t equal to 0, the height in the tank is h. At time t, we need h by 4. So in this complete equation, the unknown is t, of course, okay. So t is equal to minus A1 by A naught into 1 by root 2g into integration of 1 by root h is 2 times of square root of h, 2 times of square root of h by 4, which is h by 2 minus root h, clear, okay. So this is the value, of course. So which means this 2 can cancel this square root of 2 times A1 by A0 into square root of 2 by G into root H by 2, or sorry, root H by 2, of course. Okay, so this is what we have, because this is root H minus root H by 2, so root H by 2, that's all. So now I think the values are known to you. This is the time at which the water level in the tank will fall from H to H by 4. Okay, so A1 A0, A1 is 1 meter square, so this is 1 meter square. Then what about A0? 1 centimeter square, so 10 power minus 4 meter square. G, so what is the value of G? G is 9.8. okay, so G is 9.8 actually. G is 9.8. H is the initial level of water in the tank, so measured from y equal to 0. Initially the water level H measured from y equal to 0 is 1 meter, so H is 1, so this is 1 meter. So if you do this, you'll get the answer in some seconds. Okay, and what are the units they were asking? Seconds, round off to 1 decimal place. Just do it. So this is 10 power 4, 10 power 4 into, so 10 power 4, 10 power 4, which is 10,000, into square root of 2 by 9.8 into 2 by 9.8 square root. Okay, so 4517 divided by 2, so divided by 2, so 2258.78 seconds, 2258.7 whatever. Okay, so the time which you need is 2258.77. okay, seconds. This should be the time required for the water to fill out. Okay, 2258 whatever, close. But it's a simple question actually. I have done this Bernoulli's equation to show you this V is equal to root 2GH. Otherwise, if you know root 2GH, directly you will do these 3 steps. Okay, but integrations and differentiation should be done very carefully. Okay, because many times rather than doing differentiation, people do integration, or for integration people do differentiation. They'll multiply these 2 here instead of dividing it. All these things you should not do. Okay, clear to all, everyone? So please type in the chat box, is this okay? Yes. If you have any doubts, you can ask me meanwhile. Fine. So 2258.7, let's say 2258.8 seconds. Okay, then let's solve this question. 2021 NAT. A cylindrical jet of water density 1000 cube impinges at the center of the flat circular plate and spreads radially out. Okay, so it is impinging on the center and pushing flat. So because of this impingement of the jet, this plate will be compressed to down. Okay, outwards as shown in the figure. The plate is resting on a linear spring, so it's a linear spring with a constant of 1 kilonewton per meter. The incoming jet diameter d is 1 centimeter. If the spring shows a steady deflection of 1 centimeter, so the spring is showing a steady state deflection of 1 centimeter upon impingement of jet, then the velocity of the incoming jet is dash meters per second, round off to 1 decimal place. Okay, so let's see. Let us draw the free body diagram. So the plate has some weight. Let's see, plate weight is given, impinges at the center of the flat circular plate and spreads outwards. Okay, as shown, the plate is resting on a linear spring. The velocity of the jet. Okay, let's neglect the plate weight. Okay, so there is no plate weight. So this is F due to the jet and this is F due to the spring. Under these two effects, this plate is in static condition. Okay, so this is F due to the jet and this is F due to the spring, which is equal to K times delta, where delta is the depression in this plate, and obviously if this is depressing, then the spring also compresses actually a bit. Okay, so solution, let's write given data. Given water, so density 1000, everything is done. So spring constant K, 1 kilonewton per meter, which is 10 cube newtons per meter. Okay, the incoming jet diameter 1 centimeter, so D, 10 power minus 2 meter. Spring shows a steady deflection of 1 centimeter, so delta is also 1 centimeter, which is 10 power minus 2 meters. Good. Okay, then the velocity of the incoming jet is dash. So let's see from this free body diagram, for plate, for equilibrium of the plate, sigma Fy, maybe you take the upward direction as positive, so this is 0. So this gives you ultimately the force acted by the jet is equal to K times delta. Okay, so what is the force acting on the jet? Like if you take the control volume, so if you take this control volume, the fluid is coming in this sense and leaving radially out. Okay, so which means if you have the velocity of the jet V, then this is V and this is V. So in the vertical direction, so clearly you see at all these 360 degrees, fluid just splashes horizontally. There is no vertical component of velocity. Okay, but here in the beginning it has vertical component. So m dot, which is OAV, into vertical component at inlet minus vertical component at outlet, is equal to K times delta. So now what you need, what is the final thing you need? Velocity of the incoming jet. Okay, good. So V is equal to K delta by rho A for half. So this is the velocity with which the jet should be impinged onto the plate, such that the deflection in the spring is exactly 1 centimeter. Okay, so K, this guy 10 cube Newton per meter, delta 10 power minus 2, density 10 cube, area of the jet, so jet diameter is 1 centimeter, so pi by 4 into d square, which is 10 power minus 4, this whole power half. So 400 by pi, or 20 by square root of pi. Okay, so 20 by square root of pi, 11.283 meters per second. Is it? So 11.283 meters per second is the velocity with which the jet has to hit the plate. Okay, so 11.283 whatever. How many decimals we need? 1 decimal, so 11.3 meters per second. Okay, a very straightforward question. Next, so 2022, let's see. A tube of uniform diameter d is immersed in a steady flowing inviscid liquid stream of velocity v. So this is open to PATM. So there is a stream and this tube is kept in this. Okay, gravitational acceleration is represented by g. Volume flowed to the tube. See, this is not a pitot tube, means the length of the tube is not sufficient to withstand the pressure. So if this tube length is not sufficient, then it won't act as a pitot tube, it just acts as a bypass, that's all. Okay, so some part of the fluid goes here, it moves and it comes like this, that's all. Okay, now you want what is the volume flow rate to the tube actually. Okay, so this tube is of diameter d. Okay, good. Discharge through the tube is equal to area of tube into velocity to the tube, and area of the tube is pi by 4 d square. Clearly it's a tube of diameter d, so pi by 4 d square, okay, into velocity. So all this is pi by 4 d square. In fact, you want to know what is the velocity of the flow through the tube. Okay, so how do we get that? Let's see. This is a pipe of uniform diameter. Okay, so if this is a pipe of uniform diameter, actually discharge through the tube, So let's apply the velocity here is v, for example. Okay, the velocity here is v. Then let's apply the Bernoulli's equation. Okay, let's call this v2, for example. Okay, so v2, a tube into v2. So let's apply the Bernoulli's equation at this point and also at this point. Okay, because this is one point of interest where you know the velocity, and here you know the velocity is v2. Here the velocity is not 0. Okay, there is some velocity which is going, and it's a free stream, free liquid stream. So applying Bernoulli's equation at points 1 and 2, where point 1 is this and point 2 is there, into v2. So applying Bernoulli's equation at points 1 and 2. So this implies P1 by OZ plus V1 square by 2Z plus Z1 is P2 upon OG plus V2 square upon 2Z plus Z2. Okay, now let us see the understanding of different terms. What is P1 actually here? Okay, so you see, so this is point 1. So at this point 1, if you see, the pressure is P atm plus this H1. Okay, so this is the liquid stream actually here. So P atm minus the pressure at free surface of the liquid stream. So this is the free surface. Okay, so this is P atm plus OG H1 is what you get. Of water G H1 by OG plus V1 square. So what is V1? This is V at this point. So V square by 2Z plus Z1. So let's call this Z1 as 0, for example. So if this is 0, then this point is at elevation of H1 plus H2, correct? Because with respect to 1, this point is at elevation of H1 plus H2. So if you take this as 0, then here you will get H1 plus H2 is the potential head. Okay, so plus 0 is equal to P2. So what would be P2? Here this is P atm. Okay, the volume flowed to the tube, that's all. Okay, so if this is P atm, then P atm minus OG H2. So P atm, no, this is discharging to atmosphere, is it? That's what it's done. Yeah, it is discharging to atmosphere. No, a tube of uniform diameter D is immersed in a steady flowing fluid as shown. Okay, so I think this question should be made much clear. So here this fluid is being discharged onto the atmosphere. So if that's being discharged to the atmosphere, then P atm by O water G plus V2 square by 2G plus Z2 H1 plus H2. This is what you would get actually. Okay, correct, because that fluid is going to the atmosphere. Okay, so pressure at location 2 is P atm. So if you simplify this, this term plus this H1 will cancel this full term actually, right? Because P atm by OWG plus H1, P atm by OWG plus H1. So what would be V2? V2 is equal to V square minus 2G H2 under square root. So this is the value of V2, right? So therefore Q to the tube is pi by 4 D square into root of V square minus 2G H2. That's all. Okay, so root of V square minus 2G H2 should be somewhere, yeah, option D. D is the correct option. Yeah, recently someone has asked me this in the paid batch class also, but I think in the fluid mechanics last lecture someone has asked me. But it's not a pitot tube. Okay, so it's a just bypass for the flow. Clear? Any questions on this? So come on guys, any questions on this? Type it in the chat box. Clear? So D is the correct choice. So let's see again some viscous flows. The steady velocity field in a inviscid fluid flow is of density 1.5 is given as V is equal to x square y square minus x square plus 2xy j. Neglecting body forces, pressure gradient at x equal to 1 and y equal to 1 is dash. Okay, so let's see solution. Given velocity field, okay, so it's a steady, and V is equal to y square minus x square times I plus 2xy j. Neglecting body forces, inviscid, the pressure gradient at this location 1 comma 1. So if you add the equation, so density is 1.5. okay, units, nothing is given, so let's add some units. O is equal to 1.5 units. So momentum equation, O x bar minus del p plus mu times del square V plus lambda plus mu times gradient of divergence of velocity is equal to O times dV upon dt. Okay, so this is the actual equation. So firstly, steady flow and incompressible flow or not. Let's see. Dou E by dou x is minus 2x, dou E by dou y is 2x. Yeah, it's incompressible. 0. Inviscid, neglecting body forces. Okay, so these terms would go to 0. So then in this case, del p minus rho times dv by dt. So ax I cap plus ay j cap. Okay, so ax dou E by dou t plus u dou E by dou x plus v dou u by dou y. Okay, so clearly it's a steady flow field they have given you. It's a steady flow field. Then u into dou u by dou x, which is minus 2x plus v into dou u by dou y. Okay, so plus v into dou u upon dou y. So if you simplify this, 4xy square minus 2xy square, so you have 2xy square plus 2x cube, 2xy square. Okay, similarly at y, acceleration at y is how much? Dou v by dou t plus u dou v by dou x plus v dou v by dou y actually. Okay, and clearly this is again 0. So u into dou v by dou x plus v into dou v by dou y. Okay, so dou v by dou y is 2x. So if you simplify this, 2x square y minus 2x square y and plus 4x square y, so you have plus 2x square y. Okay, shortcut tricks in this case. This accelerations I don't want to share shortcuts because see, many times this is very simple thing, okay, but people do lot of calculation mistakes here in this case. Okay, so it takes time. Let's do. See, I'll tell you one thing honestly, guys. Generally, whoever asks for shortcuts, GATE is one exam where shortcuts never work. Okay, size of the problem should get small because of the concept, not because of the formula. Understood? Like let's say for example you have a Bernoulli's equation. Okay, if the pipe is flat, if the pipe is horizontal, okay, then you should know that there is no potential head. That's how the term should get zeros. Clear? It's not like you mug up some formula for that. And see, I'll ask you a simple fact. Answer me honestly. Let's say each faculty taught 20 or 15 shortcuts, for example. Okay, or let's say 10 shortcuts per subject. Okay, maximum 10 shortcuts. Let's say for each chapter, one shortcut I have taught you. Then you'll have 15 subjects. Can you remember 150 shortcuts very correctly in exam and apply them correctly? Can anyone do that? 150 shortcuts, you keep in mind, sharp, go apply all 150 perfectly, or whatever. Out of that 150, let's say some 6-7 shortcuts has come in the exam. First of all, can you remember these 150 shortcuts and 150 formulas? Never, right? So your size of the solution should come down because of the concept, not because of the formula. Got it? Now see here, this is the equation. Okay, but in this equation we know that 0 body, inviscid, divergence is 0. That's how. Clear? better do these things. See, if you start a timer, maybe I'll start a timer, and to solve that question, we maximum need 3 to 4 minutes in gate. That to not all the questions, few questions. Okay. Gate exam is set in such a way, if you start from basics, the question will be solved in maximum 3.5 to 4 minutes. Understood? And that to not every question. Out of 65 questions, you have some theoretical questions, some 1 mark very simple questions, so that maximum 4 to 5 questions will be lengthy in a paper. Okay. I've seen on YouTube people come up with solving in 10 seconds, solving in 5 seconds, solving in half second. You know, no need to solve anything, you just write the answer. IIT professors are not very, lightly taken, guys. You understand? If every question can be solved in 10 seconds, then your complete gate exam will be finished in 650 seconds, which means more than 10 minutes or less than 11 minutes. Then what you're going to do for the next 169 minutes? Understand? So please don't believe these words of like shortcuts, these techniques, tricks and all. If in some of cases the concept is not cleared, but then you should definitely start. Okay. Okay. See, gate is about the conceptual understanding. They'll test your understanding of the subject, not how well you remember the formula, to be frank. Okay. Clear? See, if I myself want to solve this question, I can solve this in 2-3 lines. Okay. But that's not the motive. It's not me solving this question. I want you guys to understand this question when I solve. Okay. I would have directly taken this is dV by dt, correct? Anyhow, I know the flow is steady, so this term is nothing but V dot del operating on V. Using this vector properties, I can directly solve this question. Okay, but my aim is not to do these things. Okay, I'm telling you guys, I've seen on YouTube and all, many people come up with this techniques. These are just the words which can catch the views, that's all. 100%. In exam nothing will work, you can try if you want. Okay, maximum you can say 1 or 2 tricks keep working. The rest of the 62 questions you will solve by understanding the things. Okay, gate prep is not like very tricky. All 65 questions involve shortcuts, or at least not even 65, not even some 15-20 questions involve shortcuts. Okay, majority above 55 questions you'll have to use your knowledge, use your concept and answer the questions. Clear? So don't believe in all this stuff, keep practicing the things. Chalo. So this is 2y cube plus 2x square y. So obviously at the point 1, 1. So if you want this at the point 1, 1, this value is 4. This is also 4. So therefore pressure gradient is equal to minus density times of 4i plus 4j. Density is given as 1.5. So minus 6i minus 6j is the pressure gradient. Okay, so that's the gradient. Clear? Mathematical calculations may get avoided in some cases, okay, but not like you. And many times I get a laugh when people just give the formula and tell that it's a concept. Formula is something different from concept. Okay, you understand the concept, you do some mathematical analysis, then you get a formula. Formula is not the concept. Clear? Anyway, let's see. So minus 6i minus 6j is what you have. Okay, so since density is 1.5 units, okay, so that's why it is minus 6i minus 6j. So let's solve this question. 2023, sometime back, last year. Solution. This velocity field V is equal to kxi minus kyj. Okay, where k is 2 second inverse. The coordinates x and y are in meters. Assume gravitational effects to be negligible. Density of the fluid is 1000, so flow of water. Pressure at origin is 100 kilopascals. So pressure at origin is 100 kilopascals. Then pressure at the location 2, 2. What is this value? That's what. Okay. Some derivations we have to understand at some points. Yeah, correct. If some of you have solved all the PYQs, you will understand that this shortcut, all these YouTube legends will fail. Okay. Anyway, let's see. So the momentum equation, plus mu times del square V is equal to rho times acceleration, so which is dou V by dou T plus V dot del operating on V. Okay. Then neglecting body force, nothing is mentioned about the viscosity, correct? So this is 0. So the pressure gradient is equal to, okay, pressure gradient is equal to minus density times, so minus 10 cube times of this velocity component doesn't involve this, so this is 0. Then x component of acceleration, okay, so v dot del is u into dou E by dou x plus v into dou E by dou y operating on x. Okay, so this gives you kx into k minus ky into 0, so this is k square x I cap plus, okay, then into minus k, that's all, correct, times j. So this gives you k square x, so minus 1000 times k square times of xi plus yj. This is what you have, okay, and k is 2, so this is minus 4000 minus 4000. Okay, so this is the value. Now if you simplify this, dou p by dou x I cap plus dou p by dou y j cap, okay, minus 4000 x I cap minus 4000 y j cap. Okay, so if you have this, then you know the pressure at the origin is 100 and the pressure at the location 2, is kilopascals. Okay, so in fact the velocity field, there is no z, of course. Okay, then you can do one thing, since you came till this point, okay, you have written minus 4000 times of xi plus yj, so dou p by dou x is minus 4000. so if x changes from 0, so you can see, if you want to solve this equation, dou p by dou x is equal to, I'll tell you one more method to solve this. Okay, so let's see, there are two methods, minus 4000 x dou p by dou y is equal to minus 4000 y, right? So can I say this as p of x comma y is equal to minus 4000 times of x square by 2 plus y square by 2 plus some constant. Okay, so this is what you get. So the pressure at this point is minus 2000 times x square plus y square plus some constant. So this would be the pressure function actually. Okay, so this is the pressure function, because you see these are the two partial differential equations. If you solve, you will get these things. Now they have given you one boundary condition to get this constant. So given p of 0 comma 0 is equal to 100 kilopascals, which would be 10 power 5 pascals. Okay, so this gives you 10 power 5 is equal to minus 2000 times 0 plus constant, so c is equal to 10 power 5 pascals. Okay, so c is 10 power 5. Then the pressure at this location, what is the point? 2 comma 2, minus 2000 times of 2 square, 4 plus 4 8 plus 10 power 5, which is in pascals, which could be some kilopascals. Okay, so 10 power 5 minus 2000 into 8, 16,000. Okay, so 84,000 pascals, so which is 84 kilopascals. So the pressure at the location 2 comma 2 is 84 kilopascals. So this is one point actually. Okay, so this is the classical way. This question is in mechanical. Okay, I have taken only all mechanical questions. Okay, not XC questions. So everything is for mechanical. So let's see, this is 84 kilopascal. So this is one classic way to solve this question, or this is the actual way, ideal way to solve this question. Since there is implicit in this question, you can do one more thing. This is one ideal way, or let point 1 be origin, point 2, because somebody has asked shortcut, okay. So this is 2 comma 2. Since assuming it's a 2D flow, because nothing is mentioned in terms of Z, so assuming nothing is changing in Z and everything is happening in the XY plane. So if you apply the Bernoulli's equation, we have by Bernoulli's equation P1 by rho g plus mod velocity at 1 square upon 2g is equal to, neglecting the potential effects, no body force and all they have given, so v2 square upon 2g, okay. So 1 is the point of origin and 2 is the point of v2, clear. So this can be solved as P1. So P1 is the pressure at origin, which is 100 kilopascal. So 10 power 5 g can be cancelled in all the terms by 10 cube plus, now what is the velocity v1? So v1 velocity at origin, if you put x is equal to 0 and y equal to 0 in this profile, you will get velocity as 0 at origin, okay. So this term would be 0, is equal to P2 by rho w plus v2 square, okay. So if you put x equal to 2 and y equal to 2, so velocity at 2 comma 2, let's see, velocity at 2 comma 2, for example, if you like velocity at 2 comma 2, this point is k times or 2k times of I minus j, this is what you get, correct. And k value is given as 1 more 2, so 4 times of I minus j, okay. So this is what you have, because k is 2 actually, correct. They are given k equal to 2 second inverse, yeah, k equal to 2. So if this is the velocity at section 2, then the magnitude of this velocity vector is 4 times of root 2 actually, okay. So square of that, 16 times 2, which is 32 by 2 is what you get. Did you all get this value? Did you all understand? How did I do this? You apply the Bernoulli's equation, because they told you body forces, gravitational forces are not there. So let's eliminate the potential heads, okay. So if you eliminate the potential heads, then what do you get? P1 by rho plus v1 square is 0, because if you put origin there, velocity vector at origin is 0, okay. So no magnitude in this case. P2 by rho w plus v2 square, okay, and v at the location 2 comma 2 is given by this velocity vector, so square of this. So if you simplify this, P2 would be in pascals, so 100 16, so 100 minus 16, 84 into density of water, so 1000 pascals. So P2 is equal to 84 kilopascals. This is the way when the potential heads are neglected, of course, okay. So you can follow any one of these techniques to get clear. Normally this is a mathematical way for any profile, because if someone asks me what is the pressure equation, okay, then we should be able to know. Clear? Because once I know this equation, x is 2000 times of x square minus y square plus 10 power 5, I can calculate pressure at any location, not only at 2 comma 2. Fine. Is this question okay to all of you? Both the methods. 84 kilopascals is going to be the pressure at the point 2 comma 2 in the flow field. Okay. Okay, 84. So let's see 2023 again, 2 years back. Solution. Consider a unidirectional, means there is only u component for this flow field of the with the velocity field given by x, y, z is equal to u of x comma t, okay, times I cap, where u of 0 comma t is equal to 1 if the spatially homogeneous density field varies with time as rho of t is equal to 1 plus 0.2 e power minus t, then the value of u of 2 comma 1 is dash. This is a fluid question from fluid mechanics, of course. Okay, so let's see, it's in mechanical again. So given velocity field is equal to u of x comma t I, and you have the boundary conditions u of 0 comma t is equal to 1, means at any time always the velocity at x is equal to 0 is 1 unit. Okay, if the spatial homogeneous density, so density change with the time is 1 plus 0.2 e power minus t, then value of this function at 2 comma 1, assume all quantities to be dimensionless. Okay, so everything is non-dimensionalized quantities. Good. So let's see, we have dou rho by dou t plus divergence of rho v is equal to 0, correct? This is the continuity equation. Okay, so spatially homogeneous means the density do not change with x, y, z. Okay, it's like a lumped system. Density changes only with time but not with space. Okay, that's what you mean spatially homogeneous. You understand? Like let's say at time t equal to t, if this body is what you have, okay, some mass or some flow which is happening, then at this point and at this point the density is same at any given time. Okay, but at different times the value at this point may not be equal to this value previous. Like let's say at time t equal to 10 seconds it is 5 kg per meter cube, 5 kg per meter cube, but at time t equal to 12 maybe this is 13 and this is 13. Okay, but whatever is the change, it changes uniformly throughout. Okay, that's the meaning of spatially homogeneous. Now let's see, this can be written as, since v is having only u component, so this can be written as dou by dou t plus dou by dou x of rho into u is equal to 0. Okay, because v and w components are not there. So derivative of dou by dou t is minus 0.2 into e power minus t plus this density is not dependent on x. Okay, so it only depends on time. So if you take this out, 1 plus 0.2 into e power minus t, sorry, this is e power minus t into dou u by dou x is equal to 0. Okay, now how do you calculate the value of u of 2 comma 1? So we can write this equation, dou u by dou x is equal to .2 e power minus t upon 0.2 e power minus t upon 1 plus 0.2 e power minus t. Okay, so this is what you get. So let's solve for u. U is equal to u of x comma t is equal to, if you integrate with respect to x partially, then 0.2 e power minus t by 1 plus 0.2 e power minus t into x plus some function in terms of t. Why? Because this u is only function of x comma t, so if you integrate this you'll have this function. Okay, now let's see, u of 0 comma t is 1. So given the boundary condition, to get this, u of 0 comma t is equal to 1. This implies at x equal to 0 comma t equal to 1, u is actually 1. So if you simplify, 1 is equal to, if you put x equal to 0, this term is 0 and you have f of t. That's all. Okay, so f of t is 1, of course. So therefore what is u of x comma t? X times 0.2 e power minus t by 1 plus 0.2 e power minus t plus 1. So that's the non-dimensional full velocity field. Okay, and you need some point to calculate this value. What is the point? 2 comma 1, u of 2 comma 1. So therefore at 2 comma 1, so u of 2 comma 1 is equal to, because this is time domain, okay, and this is spatial domain x, so x is 2 times 0.2 times e by 1 plus, sorry, this is e power minus 1, 0.2 e power minus 1, this plus 1, so units. That's all. So you need to do this calculation little carefully. So let's see, first let's get this value, e inverse. Okay, so e inverse, so let's save this value, that's e inverse, then e inverse into 0.2 E inverse into 0.2, this value divided by 1 plus 0.2 into E inverse, 1 plus 0.2 into E inverse. Okay, so this is the value into 2 plus 1, so 1.137 units. That's all. Okay, U of 2 comma 1 is equal to 1. Okay, 1.137 units. Clear? Is this okay to all of you? And few people, they wish to write this as take this 0.2 e power minus t common, then this will be 1 by 1 plus 5 e power t. Okay, people do it, whatever you do, this is the way to solve this. Okay, because see, if you take 0.2 e power minus t common, then you'll have 5 e power t here, so 1 by 1 plus 5 e power t would be the value. Then if you put t equal to 1, 1 by 1 plus 5 times e. Okay, so that calculation can also be done, but whatever you do, you should get this values, 1.137 units. Okay, fine. So let's go to the next question quickly. Sprinkler 2018. Okay, I think this kind of question we have solved in the class. Chalo. A sprinkler shown in the figure rotates about its hinge point in a horizontal plane due to water flow discharged through its 2 exit nozzles. The flow rate Q through the sprinkler is 1 liter per second and the cross sectional area of each exit is 1 centimeter square. Assuming each flow rate through both arms, equal flow rate through both arms and a frictionless hinge. At the hinge there is no friction, so this is the hinge. So this is the hinge. Okay, then the steady state angular speed of rotation, of the sprinkler in 2 decimals is dash. Okay, so this sprinkler is rotating clockwise actually. Okay, so the sprinkler, Mahavishnu, this question already solved. Yeah, their arms are pointing in the different direction. Okay, and here depending upon the moment, the arms are pointing in the same direction. Clear? Fine. And even you can sense that this arm is rotating clockwise. Okay, why? Because see, whatever the linear moment that's going here, same is the linear moment that's going here. But if you take the reaction force momentum, if you take the reaction force moment, this is the reaction force and this is the reaction force. These reaction forces are same. Okay, but at this place the reaction force has a larger arm, so definitely this moment will be dominating. As a result, sprinkler rotates clockwise, which they have already given in the question, kind people. So they have already given in the question that it's rotating clockwise. Okay, but even if they don't mention the rotation direction, we should sense that this rotation is in clockwise direction, because I hope you understand the reaction forces would be same at both the cases. Okay, but you have a larger moment at this case. Okay, so that's why sprinkler rotates. So let's say the rotational speed is omega, then solution. So what we need, a sprinkler shown in figure rotates about its hinge point in a horizontal plane due to water flow due to discharge. The total flow rate Q through the sprinkler is this. Assuming equal flow rates through the arms, the steady state angular speed rotation of the sprinkler. Okay, so sigma T on sprinkler, which is in this case on sprinkler by fluid. No external torques, no reaction at the hinge, so this is 0. Okay, so that's what you have. So this tells you, since you have two, let's say you take the points as 0.1, 0.2 maybe, and 0.3. So these are the 3 locations where the fluid is cutting the control volume. Okay, because sprinkler is the control volume, at 1 point it goes, and 2, 3 it comes up. Okay, so it is on the sprinkler, so summation of m dot v into r at outlet, where this v is the tangential velocity. Okay, this is at inlet, minus summation m dot vw into r at outlet is equal to 0. That's what you have. Okay, so then at inlet the radius is 0, So at inlet there is no radius for the sprinkler, so no radius for the momentum which is coming in, so this R in is 0. So summation, so minus of this is equal to 0, so therefore summation at section 2 m dot VWR at section 2 plus m dot VWR at section 3 should be 0, of course. Okay, that's what this tells you, because we have two outlets, one at section 2 and the other one at section 3. Okay, so this is what you get. Now this can be written as m dot 2 into tangential velocity at section 2. So what would be the tangential velocity at section 2? At this point, if the fluid is going out with velocity v and this sprinkler is also evolving in this positive direction, then the fluid, this sprinkler is also moving in this direction. I mean, this sprinkler is rotating clockwise, so this arm and the fluid are in the same directions. So v plus this r2 into omega, so v plus r2 times omega, okay, plus m dot 3 m dot, sorry, we have r2 multiplication here, into r2 plus m dot 3. Now in this case fluid is moving in this direction but arm is coming back, so v minus r omega, v minus r times omega into 0.2 is equal to 0. Okay, now this m dot at this point and at this point is same physically. Okay, so because the discharge is being equally split, so whatever the fluid that's going out here, same would be the fluid which is going out at this case. Okay, so this, if you cancel up, what are the things we are given? Total flow rate Q is 1 liter per second. Good. So still anything we can cancel, maybe 0.1 you can cancel from the remaining terms, so this is 2. So v plus 0.1 omega plus 2v minus 0.2 omega is equal to 0. So v plus 2v is 3v, 0.1 minus 0.4 is 0.3 times omega. This is the equation, correct? Because you see this is v plus v into 2, so total 3v, 0.1 into omega minus 2 times of 0.2 which is minus 0.4, so this is what you get, 0.1. So omega is equal to 10 times of velocity to each section. Okay, what is the velocity to each section? So this is the final result whatever we got. So the angular velocity of the sprinkler is 10 times the jet exit velocity. Okay, so omega is equal to 10 into discharge to each q by 2 by pi by 4 or area of the exit. Did they give area of the exit directly? Cross sectional area of each exit is 1 centimeter square. Good. So this is 10 power minus 4 meters square. Okay, so this gives you omega is equal to 10 into discharge. So what is the discharge? 1 liter per second. So 1 liter is 10 power minus 3 meter cube per second by 10 power minus 4 actually here. So this gives you 50, I think. That's all. Okay, so 50 radians per second is the rotational speed. So that's the steady state angular speed. Okay, is this clear to all of you? It's a question from basically 2021, no 18, yeah. So is this clear to all of you? So 50 radians per second is the rotational speed of the sprinkler. Okay, sorry, 50 radians per second. So if you convert to rotations, then you can convert basically by multiplying into omega equal to pi n by 30. So 1500 by pi, if you do, so 475 rotations per minute almost. Okay, which is like 8 rotations per second approximately. So let's solve this. 2015, sometime back. 3 parallel pipes are connected at the two ends, having flow rates Q1, Q2 and Q3 respectively, corresponding frictional head losses being HL1, HL2 and HL3 respectively. Correct expression for the total flow rate Q and frictional head loss across the two ends is dash. Okay, so it's a parallel combination. So for parallel combination, come on, tell me. for parallel combination. So let's say if you have okay, so you know first path, second path and the third path, Q1, Q2, Q3 and this is Q. So just enter the answer. So first the total discharge is sum of 3, so it is not series combination, so these two are wrong. Okay, then coming to the head loss, the head loss in each path has to be same, correct? So this is in series, but B is the correct answer, of course. Okay, flow rate Q and the frictional head loss across the ends. Okay, so B is the correct answer. Discharge should be sum of the discharges and head loss should be equal in all the parallel circuits. Previous answer is 10. This one, did we miss something? M dot 2 V plus R omega, so 0.1 omega into 0.1 plus M dot 3 into V minus R2 omega, correct, into 0.2 is equal to 0. So M dot 2 is same as M dot 3, that gets cancelled. So this is 2, okay, 0.1 omega minus, this answer is given 10 radians per second, Vivekanand, V plus 0.1 omega into 0.1 plus M dot 3 into V minus 0.2 omega into 2. So V plus 2V is 3V is equal to 0.1 minus 0.4, so 0.3 omega. So this is 0.1, so omega is 10 times V. Okay, omega is 10 times V. So velocity through each exit is discharge by flow area. Okay, so discharge and flow area are given 1 liter per second, so 10 power minus 3. Velocity is discharge by area, correct? Yeah, Q by 2 by, this is 1 centimeter square at each exit, correct? So half into 10 power minus 3, half into 10 power minus 3, 1 by 0.0250, but the calculation is matching up. Any external torques? No external torque, obviously. Friction at hinge is 0, frictionless hinge. Steady state angular speed of rotation in radians per second of the sprinkler. Radius at inlet is 0. At outlets, M dot 2 and M dot 3 should be same because it's equal splitting of the discharge. V plus, this is 10 centimeters and that's 20, correct? V plus 0.1, check the official key once. 9.5 10.5 is the answer range, but how come? This is standard RTT, so sprinkler shown rotates about this hinge point. This is going up, correct? So if this is coming down, then V minus 0.2 omega, here the relative velocity is V plus 0.1 omega into R2 is 0.1, that R3 is 0.2 is equal to 0. M dot 2 and M dot 3 gets cancelled, that's okay. Then 0.1 cancels 0.2 2 times, means if you take 0.1 common, that's the equation. So 3 times V is equal to, so V plus 2V, 3V is equal to 0.3 times omega. So 0.1 omega is 10 times V, and velocity to each section is half of the discharge divided by area, correct? V is equal to Q by A. So this is 1 liter is equal to 10 power minus 3 meter cube per second by each exit nozzle, 10 power minus 4. So 10 into Q by 2 by 10 power minus 4. So 10 into 10 power minus 3 by 2 by 10 power minus 4. So but I'm getting 50. Absolute velocity is of 2 and the opposite. Sorry, absolute velocity is of 2 and the opposite. Didn't get you. Absolute velocity at is of 2 and the opposite. This is fluid and this is the sprinkler direction. So this should be V plus 0.1 omega. No, this equation is correct actually. You want to say this is -1 and this is +1? No. M dot 2 times of V plus 0.1 omega into 0.1 plus M dot the mass flow rate. It should be 50, right? Yeah. But how come they have given 10? See, because here this fluid is moving in this direction and the tangential velocity of the sprinkler is also in the same direction. Okay. Minus M dot V3, is it? Oh, correct. Just a second. If you look at these things, okay, at R in and R out, then this torque because of this exit is clockwise and this because of this is anti-clockwise. So there should be minus here. Yeah, I misjudged. It should be minus at this point. Then let's do this calculation again. 2, because you see, when you take this sigma torque about the z-axis, 2, okay. Oh, sorry. Just give me 1 second. Let me erase this. Yeah, because I missed this sign convention. Just a second. These velocities are correct, but there should be a minus sign here because here the assumption is maybe you can take the anti-clock sense as positive. Then if you take the anti-clock sense as positive, anti-clock sense as positive at all the cases, then this is having a clockwise sense. So there should be a minus sign here. Okay, it should be minus. So minus of V plus 0.1 omega plus 2V times or 2 times of V minus 0.2 omega. This is 0, 2. This should be minus sign because one is clockwise moment, 2. Okay, this is clockwise moment, sorry, because this jet has the angular momentum in the clockwise direction and that has the anti-clockwise moment. So this, if you simplify now, 2V minus V, then minus 0.1 minus 0.5, so is equal to 0.5 times omega, correct? So V is equal to, omega is equal to 2 times V is what you get, right? Omega is equal to 2 times V. So omega is equal to, it's not 10 times V, it's only 2 times V. Okay, so 2 into Q by 2 by area. So 2 gets cancelled. So Q, 1 liter per second, is 10 power minus 3 meter cube per second by this is 10 power minus 4 meter square. Correct. So 2, of course this is just the magnitude. So if you simplify this, you'll get 10. Yeah, sorry, this should be 10 radians per second. Yeah, we missed the sign convention here. This should be negative. Okay, no, these velocities are V plus 0.1 and V minus 0.2. These are correct. Okay, because the same direction will have. Okay, but the moments are opposite. Okay, so it should be minus of the moment due to this. Like if you take the anti-clockwise sense of moment to be positive, then since this angular moment is in the clockwise sense and this angular momentum is in the anti-clockwise sense, so you should subtract. Okay, so for this anti-clock convention to be positive, the first term is negative, so this would be the value. Okay, so 10 radians per second should be the correct answer. Yeah, this minus sign we have missed. Okay, you should be careful in choosing the sign conventions. Okay, like how the velocity along the positive x direction is taken as positive, negative x is taken as negative. So similarly here we have these things. Okay, reaction will be opposite to that of the water direction, sir. Too, but the hinge has no reaction. No, the hinge is a frictionless hinge. secondly, this is on the control volume. Okay, so on the control volume or on the fluid, if we take this sign notations, then this should be minus and this should be plus. Okay, you understand, like the net effect, if we assume that the net torque is in the anti-clock sense to be is positive, then what you took same in section 2, where obviously, see guys, it's very simple. Look, if you have the rotation in this case, okay, in this sense, if you have the rotation, then this fluid is going in this direction. Okay, if the sprinkler is rotating in this direction, the arm velocity is also in this direction. Okay, now since the jet and the arm are moving in the same direction and they are in contact, so you get a plus sign. Okay, similarly here, this jet is coming in this direction, but the arm has tangential velocity in the opposite direction, so V minus R2 omega. Clear? So that's how the velocity is. And obviously the moment, the fluid is coming in this direction and the sprinkler is also going in this direction, whatever. So here, if you take the moment of this momentum is in the clockwise direction. Here the moment of the momentum is in the anti-clockwise direction. So this is positive and this is negative. Okay. And normally if you take the general convention, the anti-clockwise sense as positive, then definitely there should come a minus sign here. Okay. So it should be 10. Sorry, I have missed this minus sign. That minus should be there. So it should be only 10 radians per second. Yeah. Fine. Any doubts? Is this question okay to all of you? There should be a minus sign here, obviously, because the sense anti-clock moments are positive. Okay, or if you take clockwise sense as positive, then this becomes plus and this becomes minus. So mathematically the equation still remains same. Clear? Okay. All of you, just confirm the understanding. Did you all understand why there should be a minus sign here? Because the moment generated due to the momentum going through the section 2 is clockwise in the sense. Okay, but the general convention is anti-clockwise to be positive. So this first corresponding to section 2 you have positive negative moment, and section 3 it is positive moment. That's all. So this is done. So let's see this question. A smooth pipe of diameter 200 mm carries, it's a 2010 long back question. Okay, a smooth pipe of diameter 200 mm carries water. The pressure in the pipe at section 1, elevation 10 meters, is 50 kilopascals. At section 2, S2, elevation is 12 meters. Okay, this is pipe of diameter. The pressure is 20 kilopascals and 2 meters per second at section 2. Of course, the density of water is 1000 kg per meter cube and acceleration is 9.8 meters per second square. Which of the following is true? Flow is from S1 to S2 and head loss is this. Flow is from S2 to S1. Head loss. Okay, so head loss difference and flow direction. These are the things which we have to answer. Okay, so let's see. Solution. Given section 1 parameters. Okay, so at section 1 what's happening? A smooth pipe of diameter 200 mm. So D, first of all, diameter is 200 mm, so which is 0.2 meters. Okay, so this should be 0.2 meters. Okay, so section 1, what are the conditions? The pressure in the pipe at section 1, this elevation is 10 meters, is 50 kilopascals. So P1 is 50 kilopascals. The elevation Z1 is 10 meters. Okay, so elevation is 10 meters. At section 2, elevation is 12. Section 2, this elevation is 12 meters and P is how much? So this P2 is 2 meters per second. Okay, sorry, pressure is 20 kilopascals and this is a uniform pipe. Okay, because you see of diameter carries water, so this smooth pipe of diameter 200 mm carries water. Okay, so D is 200 mm at both the sections. Okay, then what about the velocity? 2 meters per second. So V is 2 meters per second at this point. Okay, so V2 is 2 meters per second till this point. Density of water is 1000, so rho is 10 cube meters per second. Okay, and acceleration due to gravity is 9.8, so G is 9.8 meters per second square. So what is the flow direction? Okay, so first this is section 1, section 2. What is the flow direction from section 1 to section 2? That's the question. So let us calculate the total head at section 1. So total head at section 1, because you know fluid always flows from high head to low head, so H1 is P1 by OG plus V1 square by 2G plus Z1. Okay, clearly this kinetic head has to be same at both inlet and outlet. Okay, why? Pipe is of uniform diameter and incompressible flow, so if you apply continuity equation, V1 should be equal to V2, correct? So V2 is same as V1 from continuity. Okay, so this term is equal to P1, which is 50 kilopascals by rho G, G is 9.8 whatever, plus V1 square by 2G, so 4 by 2G, plus this is at an elevation of 10 meters. So if you calculate the total head available at this point, let's see, so 52 by 9.8, 52 by 9.8 actually, because G is given 9.8, 52 by 9.8 plus 10, so this is 15.306 meters. This is the total head which is available at section 1. Okay, so this is at section 1, 15.306 meters. Then total head at section 2, H2 is P2 by OG plus V2 square by 2Z plus Z2, so which is P2 by rho G plus V2 square by 2Z plus Z2. So this is the elevation at section 2, of course. Okay, so if you again simplify this, this is 22 by 9.8 plus 12, so 22 by 9.8 this value plus 12, so 14.245, 14.245 meters. Okay, so clearly the head, total head available at section 1 is that, and total head available at section 2 is this. Okay, so fluid always flows from high head to low head. Many times people say this word like fluid flows from high elevation to low elevation. That is generally only when the pressure is uniform, all this stuff. Okay, but in reality, in case of pipes, the fluid always flows from high head point to low head point. Okay, and so clearly since H1 is greater than H2, this implies flow is from section 1 to section 2. Okay, flow is from section 1 to section 2. Okay, so flow is from section 1 to section 2. And what is the head loss? HL, when it's flowing from H1 to H2, this loss is given by this, so 15.306 subtract from here. Okay, so 15.306, 1.06 is the head loss meters. So the head loss during this flow is from 1.06 and flow is from section 1 to section 2. So these are the two salient points in this complete analysis. Got it? Yeah. So section 1 to section 2, first flow is from S2 to S1. No, sorry. So flow is from S1 to S2, head loss is not 0.53, so 1.06 meters. C is the correct option in this case. Okay, clear? Is this okay? Clear to all of you? Come on, please type in the chat box. Yeah. So this gives you the flow direction and the total head loss. Okay, next, solve this question. Water at ambient temperature flows, means ambient like density is 1000, flows through a horizontal pipe of uniform cross section at a rate of 1 kg per second. If the pressure drop across the pipe is 100 kilopascals, then the minimum power required to pump the water across the pipe in watts is dash. Okay, so 2017. So let's see solution. Water, so given density of water is equal to 1000 kg per meter cube. Okay, so at ambient temperature flows through a horizontal pipe. So horizontal pipe, no potential heads, horizontal pipe, uniform cross section at a rate of 1 kg per second. Then the power required to pump the water. Okay, pressure drop across the pipe, delta P is 100 kilopascals because of the friction, clearly. Okay, no need to calculate the dynamic viscosity, everything is not given, so just it's a PYQ, delta P is given directly. Okay, in case if you have attended any of my this comprehensive courses in the paid batches, now you can see these PYQs are very easy compared to the kind of questions we solved in classes, then DVPs. These were pretty hard compared to these questions. Okay, so let's see. Power required to drive the flow is equal to rho g q into head loss per unit weight. Okay, so this rho q into HL, if you see this rho g into HL is q times delta P, and this q can be written as m dot by rho into delta P, that's all. Okay, so therefore power that you need is equal to m dot delta P upon rho actually. So you know you need three things, all these three things are given. So m dot is 1 kg per second, then delta P 100 kilopascals, so 100 kilopascals, so 10 cube, by density which is 1000, so this is also 1000, so 100 watts is the energy that you should pump per second, or the power required is 100 watts, which is required to drive the flow actually. Okay, so is this clear to all? Okay, fine, it's okay to all. Everyone type in the chat box, is this okay? Any doubts, or is it okay to all till this point? Yeah, just solve the same question in the test series in the morning. Acha, okay, but anyway it's a straightforward question. 7 PM से another session है, ठीक है, maximum 5:45. Okay, I'll stop. So let's see 33. I thought of solving some good 40 questions. Okay, that would be clear. Remaining questions, let me count. 1, okay, I'll do one thing, I'll skip the easy questions and we'll solve the tough questions. Okay, which would be save some time to us. Okay, because there are plenty more questions I have put, but it's okay, I'll solve some tough questions, like not tough but relatively tough questions comparatively. Okay, and easy questions I'll leave. Okay, which generally majority of the population are okay with that. Fine. So let's see, in a fully developed turbulent flow, to a circular pipe, it's a turbulent flows question, to a circular pipe, a head loss of H1 is observed. The diameter of the pipe is increased by 10% for the same flow rate, and a head loss of H2 is noted. Okay, for the same flow rate, the diameter is increased by 10% and a head loss of H2 is noted. Assuming friction factor for both the cases of the pipe flow is the same. Okay, so friction factor is same. Right? So please solve all now. We'll manage. This has taken only 28. What is 28? I didn't get. Okay. Fine. See, I can keep solving, but if you have another session, then we should not flash it. Okay. Chalo. Let me have some water. Okay. So maybe after this, I'll meet you all in gate before gate. Maybe. Okay. So we'll see. Okay. So let's see. Solution. Fully developed turbulent flow through a circular pipe, head loss H1 is observed. The diameter of the pipe, so initial loss or H1 is what you have. Then D2 is equal to, is increased by 10%, so 1.1 times D1. Okay, for both the cases. For the same flow rate. Okay, so flow rate Q1 is same as Q2. Good. So this definitely tells you velocity 1 is same as velocity 2. Okay, is noted. Assume friction factor. Assume friction factor for both the cases of the flow is same. So F is same. Okay, so F is same. F1, which is function of some Reynolds number. So this has to be same. So with this obviously implies this condition again. So V1 equal to V2 because V average D by mu. Okay, I think just a second. Discharge is same. Okay, V1 is not equal to V2 because diameter is changing. No, so sorry. Only discharge is same. That's all. Okay, so Q1 is equal to Q2. That's all we know. Okay. Then if you see this pi by 4 D1 square V1 is equal to pi by 4 D2 square V2. V average. Okay, of course. V average 1 is equal to V average 2. Fine. So the friction factor is same in both the cases. So F1 is equal to F2. Okay. So then let's see how do we get H2 by H1. So H2 by H1. So what is H2? F2 L2 V average square by 2G D2 into 2G D1 by F1 L1 V average square at case 1. Okay, so then if you simplify this, 2G and this 2G gets cancelled. This friction factor F is same in both the cases. Length of the pipe is not changed, so this can be written as V average 2 by V average 1 whole square into D1 by D2. But this V average 2 by V average 1 is nothing but D1 by D2 whole square. Okay, so this can be written as D1 by D2 whole power 4. Right, that's the idea. Like you can see, this V average ratio is D1 by D2. So this is D1 by D2 power 4, because you see clearly this V average 1 by V average, okay, V average 2 by V average 1 is D1 by D2 whole square. So since there is one more square, so this is power 4. So D1 by D2 power 5. H2 by H1, no? Yeah. Is D1 by D2 power 5. So which is D2 is 1.1. So 1 by 1.1 power 5. Okay. So 1 by 1.1 power 5. power 5, okay, 0.6209. So HL2 by HL1 is so what is this value? 0.621, okay, 6209, so 621 whatever, okay. So 2 decimals 0.062, sorry, 0.62. So that's the correct answer, okay. B is the correct answer, of course. 0.62. Hello. Let's solve this one more question. Consider fully developed flow in a circular pipe with negligible entrance length effects, of course. Assuming mass flow rate, density and friction factor to be constant, if length of the pipe is doubled and diameter is halved, head loss due to friction will increase by a factor of, okay. So again, so let's see solution. You know, H is equal to FL V average square by 2GD. So instead of this velocity, let's write it as 16 Q square by pi square d power 4 by 2GD. So this gives you, this is 8, okay. So 8 FL Q square by pi square d power 5 times G, okay. So this is the thing in terms of F, L, Q square, pi square, whatever, okay. So let's see in this what are the things which are constants. 8 is a constant, pi square is a constant. Then fully developed flow in a circular pipe, of course it has some diameter. Assuming the mass flow rate m dot, which means this is constant. So if m dot is constant, then the discharge is constant, okay, because m dot is equal to rho q, and density, it's incompressible flow, so density is constant, so q is constant. Friction factor F is also constant, G is constant, good. So if the length of the pipe is doubled and diameter is halved, then the head loss, okay. So HL2 by HL1 is equal to L2 by D2 power 5 into D1 power 5 upon L1 actually, okay. So that's what you get, L2 by L1 into D1 by D2 power 5. So if you simplify this, length of the pipe is doubled, diameter is halved, then 2 power 5 is 32 into 2, 64. So this is 64. So HL2 is equal to 64 times HL1, okay. So D is the correct answer, okay. So it should be 64 times, the head loss should increase, okay. So 64 is correct answer in this case, okay. Then let's solve one more question maybe. Consider fully developed steady state fluid incompressible flow. Consider fully developed steady state incompressible laminar flow of a viscous fluid between two large horizontal plates. The bottom plate is fixed and top plate is moving, quiet flow. Separation between the plates is 5 mm, no pressure gradient, fantastic. So linear velocity profile, okay. The density of fluid is 100 and kinematic viscosity. Average shear stress in the fluid is dash. A very straight simple question. It's based on the quiet flow, okay. A fixed plate and a moving fluid, of course. Sorry, a fixed plate and one moving plate, okay. So that's what they have given. It's a question from 2021 recently, okay. So let's see. Fine. So you have, this is fixed plate, so y is equal to 0, and this is y axis, so this is y is equal to h, okay. So let's see. Fully developed steady state incompressible laminar flow of viscous fluid between two large parallel horizontal plates. The bottom plate is fixed and top plate moves with a constant velocity of u is equal to 4 meters per second, okay. So this is u, and given u is equal to 4 meters per second, then separation between the plates is 5 mm, so h is 5 mm, very small gap, so 0.5 into 10 power minus 3 meters, okay. So this is 5 into 10 power minus 3 meters. Then after, there is no pressure gradient, fantastic. So dp by dx is equal to 0, so it's purely inertia that's causing the flow. So dp by dx is 0, no pressure gradient. The density of the fluid is 800 kg per meter cube. Density of the fluid is 800 kg per meter cube. Then kinematic viscosity is 1.25 Stokes. Okay, so lot of story they told. Okay, then the average shear stress in the fluid is dash pascals. Look, if you have normally, what is the velocity profile? Generally, the velocity profile is given by u by u infinity or u by capital U, means u of y by capital U is equal to, again people will think like this, u by capital U is equal to y by h plus alpha times y by h into 1 minus y by h. So this is the actual velocity profile, right? We'll see this. So what about alpha? Dimensionless pressure gradient 2 mu u minus dp by dx. Okay, so this is dimensionless pressure gradient. Okay, so then this term is 0 in this case, so which means alpha is 0. So if alpha is equal to 0, this is the linear velocity profile. Okay, so u is equal to u y by h. So this implies tau at the tau is equal to mu into du by dy at any given location. So tau is mu into, if you differentiate this with respect to y, you will have just u by h. That's all. Mu is constant, u is constant, h is constant. So there is a uniform shear field in the flow. Okay, this is called as zero pressure gradient flow or simple co-ed flow actually. Okay, so then tau is equal to mu. Mu can be written as rho into kinematic viscosity. So rho times nu into u by h. We need 4 variables, 1, 2, 3, 4. That's all. So let's see. Tau is equal to 800 into this kinematic viscosity guy is 1.25 into 10 power minus 4 into capital U. So capital U is 4 meters per second by this guy is 5 into 10 power minus 3. Then so 0, 10 power minus 4, 10 power minus 3. This 4 by 5 and 1.25 cancel. So 80, that's all. 80 pascals is the shear stress in the flow field. Okay, so 80 pascals is what you have. Okay, very straight calculation. 80, because this is 1.25, this is 5 by 4 by 5, so they cancel each other. Yeah, 80 pascals is the case. When I'm teaching co-ed flow, many times in mechanical, when I'm teaching batches, people question me, why are you teaching all this? This is not in syllabus. Co-ed flow is not there. Okay, this is a co-ed flow. Until and unless you don't know this velocity profile, you can't do anything. Got it? Fine. So then let's see. Okay, so let's solve this question. Two immiscible incompressible 2015. Okay, so some time back. So let's see, two immiscible incompressible viscous fluids having same densities but different viscosities are contained between two infinite horizontal flat plates. Okay, so these are the two horizontal flat plates, 2 meters apart. So these are 2 meters apart, and given this is 1 meter, so this is also 1 meter. The bottom plate is fixed, good, and the upper plate moves to the right with a constant velocity of 3 meters per second. With the assumptions of Newtonian steady, fully developed laminar, zero pressure gradient, all this stuff, the momentum equation simplifies to d square u by dy square equal to 0. See how kind people they are. They have given you the simplified momentum equation also nicely. If the dynamic viscosity of the lower fluid is mu2 is twice that of the upper fluid, means mu2 is 2 times of mu1, velocity at the interface. So what would be the velocity at this interface? That's the question. Okay, very nice people, they have given you this. Chalo. In all directions the momentum simplifies to this. Okay, so let's see solution. given d square u by dy square is equal to 0. So this clearly tells you u is some constant, let's say a into y plus b. So in both the cases, okay, because this should be a linear function, for second derivative should be 0. So let's look at the cases. Okay, if this interface is moving at uniform velocity, okay, so for interface to move at uniform velocity, fine. So this is the interface. So clearly the shear stress on the top, which is this is fluid 1 or 2, fluid 1, okay, so this is tau 1 and this is tau 2. Area of contact is same on the film on both the sides, okay. Thanks Venki. So this implies tau 1 is equal to tau 2 into areas of course, okay, and fluid the layer gets in contact on both the sides, so it's same. So tau 1 is equal to tau 2. So how do you get tau 1? So this is equal to mu 1 into, on the upper side this is a linear velocity profile. So clearly if the velocity profile is linear, then this plate is moving with velocity of the plate and this is moving at velocity of the interface, okay. So this can be written as mu into velocity of the plate minus velocity of the interface by this fluid gap, because see if u is a linear function, then du by dy is a constant, okay, so which is constant at every point, which is vp minus v intermediate by this gap is 1 meter, so 1. This should be same as mu 2 into the gradient in the second case is mu u interface minus at the bottom plate is fixed by this gap is also 1, okay. Now they have given you some more things. Mu 2 is twice that of the mu 1. So this implies u interface is equal to 1/3 times up. So the plate velocity is 1/3 times the plate velocity is 3 times the interfacial velocity. So u intermediate is equal to u of the interface is equal to 1/3 times, what is the velocity of the plate, actually the top plate, this top plate is moving at 3 meters per second, okay. That's all. So clearly this value is 1 meter per second, okay, that's all. It's a straight question, 1 meter per second, because see it's a pure understanding of maths and physics, okay. Like if you have second derivative 0, then the velocity profile should be linear. If velocity profile is linear, then du by dy is a constant, okay. So which means I can directly write the difference in velocities over the complete film, straightforward, okay. 2 by 3, why? up is equal to 3 times, no, I hope it's correct. It's fine. 1 is the answer. When is this question come up? 2015, yeah, whatever. This is fine, right? All of you type it in the chat box. It's okay, yeah. So let's see. So solve. Am I audible? Is this okay? Can you all see the screen? Yeah, okay, good then. Okay, there was a small nick here. Chalo, now it's fine, na? Okay. Actually there's a power tipping and system went shut off, I don't know why. So let's see. What is this question? Let's solve. So water flows through two different pipes, A and B, of the same circular cross section but at different flow rates. Okay, so two pipes, A and B, of course, okay, of same circular cross section but at different flow rates. Cross section is same in both the cases, so D1 is same as D2, same cross sections, so but at different flow rates. So Q1 not equal to Q2. Okay, the length of pipe A, LA or DA is equal to DB. DB. QA is not equal to QB. LA is 1 meter and that of pipe B is 2 meters. Okay, the flow in both the pipes is laminar and fully developed. If the frictional head loss across the length of the pipes is same, the ratio of this flow rates QB by QA, that's all. Okay, so head loss is same. Clear? So head loss is same, so HLA is equal to HLB. So this gives you the flow in both the pipes is laminar and fully developed. If flow in both the pipes is laminar, then it's 64 by Reynolds number. Actually, friction head loss across the pipes is same, so 32 mu QL. Okay, so let's do one thing. If you split up the terms, 64 by Reynolds number, so rho VA dA mu A L VA square by 2G dA is equal to 32 mu VL by rho G d square, whatever. So 64 into mu B by rho VB dB into LB VB square by 2G dB actually. Okay, so that's what you have. So if you simplify the things, 64 rho, 64 density, this dynamic viscosity, because fluids are same, correct? Water flows through two different pipes. Okay, then 2G is a constant in these cases. 2G is a constant. Then length of A and length of B. So LB is 2 meters and this is 1 meter, so it gets cancelled up. So V can cancel one time and here this V can cancel this one more time. So which gives you VA by dA square is equal to 2 times VB by dB square. Okay, and how do you get the velocity? Velocity can be written as discharge by area. So QA by area, which is pi by 4, so 4 times pi dA power 4 is what you would get. So 2 times then 4 QB by pi times dB power 4, that's all. Okay, so you can see this pi gets cancelled, then this 4 and 4 also gets cancelled, then you have QB by QA. Okay, so QB by QA is equal to half times of dB by dA power 4, so half into the second diameter dB by dA. Okay, so they are of same cross section, so this is 1, so this is 0.5, that's all. So the discharge is half. QB by QA is 0.5, that's what you're getting, is it correct? So you can check the key. So 0.5 is what I believe that it would be the correct answer. In fact, we have done the calculations very carefully. So dA square dB square, but dA is equal to dB, but flow rates are different, then definitely this second pipe has discharge half of the first pipe. Okay, so 0.5 is the actual answer. Clear to all of you? Webdev, Deepak, Rajendra, Shubham, Nandu, Mechanical Rockstar, Mahavir, of course, all of you. I could read only these names, rest all went. Okay, FL Q square by 12.5 d power 5, but F is not same, right? F is not same in both the cases to cancel F. Agar F same hai to then you can have the advantage of cancelling F if you apply this formula. Okay, FL Q square by 12.5 d power 5, but F is not same, so better to work out this. So then come on, solve this. 𝐂𝐤𝐡 flow is characterized by steady incompressible laminar flow through a straight circular pipe, fully developed turbulent flow, steady incompressible laminar flow between two fixed plates. No, that's plain Poiseuille. So basically here you can see this is again Poiseuille flow. Then this is plain Poiseuille flow, and this is 𝐂𝐤𝐡 flow. Okay, so D is the correct statement. Okay, so 𝐂𝐤𝐡 flow is characterized by this option D. Then let's see some more questions. Yeah, solve this question. A 1:50 scale model of a spillway is to be tested in the lab. The discharge in the prototype is 1000. The discharge to be maintained in the model test is dash. Okay, so let's see. Normally compared to actual spillway is of a dam. Okay, and compared to the actual case, the model which you make in the lab would be small. Okay, so given length of the model scale by the prototype scale is 1:50, then spillway has a free surface flow, then this gives you the Froude number between the model should be same as the Froude number between the prototype. Okay, so this gives you Vm by root GLm is equal to Vp by root GLp. Okay, and this G and G gets cancelled, so Vm is equal to Vp times root of 1 by Lm by Lp is 1 by 50. Okay, that's what you get. Then discharge to be maintained in the model test. So what is the discharge in the prototype test? Q in the prototype is 1000 meter cube per second. Okay, so this is 1000 meter cube per second, and then this discharge in the model Qm is equal to, so let's see, since Q scales to velocity into area which is of L square, so Qm by Qp is equal to velocity in the model by velocity in the prototype into L in the model by Lp whole square. So clearly this Qp can be written as, or this Qm in this case can be written as Qp, which is 1000 meter cube per second, into Vm by Vp, which is square root of 1 by 50 or 1 by root 50, into Lm by Lp whole square. So what is Lm by Lp whole square? 1 by 50 square. Okay, so this is 1000 by 2500 by root 50. So 10 by 25, of course, divided by square root of 50, 0.0565. So 0.056 meter cube per second. Okay, so this is meter cube per second. So 0.056, which is 0.0565 something. So 0.057. So that's the 0.057 meter cube per second is the value. Okay, so is this clear? Because if you look at a spillway has a free surface, so there should be a Froude number balance between the model and the prototype actually. Clear? Yes. Let's move to the next question. Oh, sorry, this has rolled up so much. So let's see the aerodynamic drag, a question from 2019. The aerodynamic drag on a sports car depends on its shape. Obviously, the car has a drag coefficient of 0.1 with the windows and roof closed. With the windows and roof open, the drag coefficient becomes 0.8. Obviously, because air comes in and there is a pressure drag that acts. Okay, so 0.8, it increases. The car travels at 44 km/h with the windows and roof closed. For the same amount of power needed to overcome the aerodynamic drag, for the same amount of power needed, okay, the speed of the car with the windows and roof open, definitely the area will decrease, okay. The density of air and the frontal area may be assumed to be constants. Okay, good. So let's see solution. Case 1, windows and roof closed. Correct. So it's a sports car, so windows and the roof closed. And case 2, let's say windows and roof open. Okay, so you have the windows and the roof open actually. Then let's see, in this case aerodynamic drag on a sports car depends on shape. Car has drag coefficient of 0.1, so CD1 is equal to 0.1, okay, with the windows and roof closed. With the windows and roof open, the drag coefficient becomes 0.8 because A enters inside, so there is some form drag which keeps acting, so it will increase expected. Then the car velocity at 44 travels at 44 kmph with windows and roof closed. So here in this case the velocity is 44 kilometers per hour. Good. For the same amount of power, so power in case 1, whatever is supplied by the engine, so same is supplied in case 2 as well. Okay, so power 2 needed to overcome the aerodynamic drag. Okay, the speed of the car with the windows. Okay, so V2, what should be the V2 actually here in this case? Okay, so let's see, whatever the power you're giving, and if the car is traveling at some uniform speed like 44 kilometers whatever at some uniform speed, then the power which is supplied by the engine is used to overcome the drag and at the given velocity. So since power is equal to drag force into velocity, so drag force half CD rho of the fluid projected area into V square into you have one more V. Okay, now in this case they have asked you to assume this power is same in both the cases. Okay, also this half is constant, the fluid and the frontal area which is perpendicular to the direction of the flow is same. Okay, so this gives you CD1 into V1 cube is equal to CD2 into V2 cube actually here. Okay, so because CD into V cube product has to be same in both the cases, and the speed of the car with the windows and roof open in kilometers per hour. So let's keep V1 in kilometers per hour, so you get V2 also in kilometers per hour. So CD1 by CD2 whole power 1/3, and clearly you know after solving this question you will get V2 less than V1. Okay, because drag has increased, so for the same power the vehicle moves at low speed. Okay, after doing the calculation, if you get V2 more than V1, your answer is wrong. Okay, you have to check the calculations. So this is 44 into 0.1 by 0.8 whole power 1/3. So clearly this gives you V2 is equal to, so this is 8, so 1 by 8 power 1 by 3 is 2, so 44 by 2 is 22 kilometers per hour. So because of opening the windows, the car speed falls to half. Okay, so 22 kilometers per hour, it's a straight calculation. 1 by 8 whole power 1/3 is 1 by 2, so 44 by 2 is 22. Okay, so we have 22 kmph is the velocity at which the car moves. Okay, then let's see this question. An object is moving with Mach number of 0.6 in an ideal gas environment, which is at temperature of 350 Kelvin. The gas constant is 320 joule per kg Kelvin. Okay, but it's an ideal gas environment. The ratio of specific heats is 1.3. The speed of the object is dash meters per second. So let's see solution. Given Mach number is 0.6. Okay, so this implies velocity of the object by acoustic velocity is 0.6. Okay, so V divided by, how do you get the acoustic velocity? It's ideal gas environment, so square root of gamma r t is equal to 0.6. So this was asked in 2021, simple question. So V is equal to 0.6 times of square root of gamma. So ratio of specific heats is 1.3 into R, 320 joule per kg Kelvin into temperature, which is 350 Kelvin. That's all. Okay, so this gives you the velocity of the object. Literally much simple questions keep coming in GATE. Okay, so V is equal to some amount of meters per second. So 320 into 350 into 1.3. So square root of this value into 0.6. That's the Mach number. So 229 almost. So 9 meters per second. Okay, so that's basically the nearest integer block. Yeah, 228.9, but if you round off to nearest integer, 229. Okay, so let's solve one more question. Consider adiabatic flow of air, again compressible flows. Consider adiabatic flow of air through a duct. At a given point in the duct, velocity of air is 300 meters per second, temperature is 330, pressure is 180 kilopascals. Assume that air behaves as a perfect gas with constant Cp, stagnation temperature at this point. Okay, so how do you get the stagnation temperature? Like, you see, T stagnation is T static plus V square by 2 Cp. Correct? This from the steady flow energy equation we have seen even during the Mach revision time. So what is the static temperature at this case? 330 plus the velocity of the air 300 by 2 into Cp. So 1.005. So 1005. That's all. So this would be in some Kelvin. So let's see, 300 square by 2 into 1005. Okay, so 44 plus 330. So 374.77 Kelvin. So this is the T stagnation temperature. Okay, this expression we have seen how to derive this and all. Anyway, if Mach number is given, you can convert this in terms of Mach number, all this stuff. Okay, like in general, if you have the Mach number, we know T stagnation is equal to T stat times of 1 plus gamma minus 1 by 2 Mach square. That's all. Okay, we have seen these expressions long back. So we'll do one thing, we'll wind up the class here. I think we have solved some good enough questions, but anyway, you have the PYQs all available. So these are some good PYQs where at a lot of points, especially in hydrostatic forces, when you have multi-layered fluids. Okay, we have done a lot of mathematical oriented questions given the velocity profiles and all. So the next PYQ session would be on 14th of Jan, Tuesday, by Sandeep sir, heat transfer PYQs. Okay, and as usual, like I think yesterday we have the Mach revision schedule 1. So manufacturing process. So today you will be having Abhyas, I think. So next today we have the manufacturing process part 1 Mach Abhyas session. Okay, so and tomorrow also you have the again the PYQs session. So do attend all these sessions. Okay, these sessions will greatly help you out. Okay, and then PYQs solving will definitely give that 5-10 extra marks. Clear? You'll have a lot of conceptual clarity like you might have got when we were solving some questions. So how to solve the arm launch sprinkler problem? I have solved it in the fast track course last year. So you can see, just take one arm, the same thing happens at all the 3. Okay, so net angular momentum at one arm is equal to 0. So from there you will get it. Okay, maybe I have one question which I solve in all my classes. I'll post it in the Telegram channel. Okay, the arm launch sprinkler problem with solution. Okay, normally I solve it in all my courses. People know whoever has attended, so we'll do it that way. Fine. So thank you all. We'll meet sometime before GATE exam again. Okay, thank you.